Glorious. Unacademy Combat. Compete, crack, conquer.
A challenging GATE contest engineered to give you an experience like none other.
Where you put your knowledge to test
and battle it out with a test
To bring out the best in you, Unacademy Combat is the most competitive, gamified contest for GATE till date, with the best of the questions by best educators.
with detailed video solutions from top educators right after each contest.
Combat live with peers to get real-time rankings and win big.
Participate in every contest to improve your ratings.
Challenging contests every fortnight or alternate Sunday. Live ranking after every question. Big rewards for top rankers. Your passion to crack GATE deserves this. Your hard work towards your dream deserves this. Fuel your inner fire for the ultimate GATE challenge. Unacademy Combat. Register now.
वेलकम बैक गाइस, कैसे हो आप लोग। सो वंस अगेन वेलकम टू दिस मैराथन सेशन एंड वेलकम टू अनअकैडमी। मैं हूं आपका दोस्त ऐश्वर्य, पढ़ाता हूं आपको गेट ईएससी के लिए। आई हैव डन माय मास्टर्स फ्रॉम आईआईटी दिल्ली एंड बीटेक फ्रॉम जामिया मिलिया इस्लामिया। 4 टाइम्स आई हैव क्वालिफाइड गेट विद माय बेस्ट AIR 226। 7 सालों का टीचिंग एक्सपीरियंस और 2 सालों का इंडस्ट्रियल एक्सपीरियंस भी है मेरे पास, और मैं कवर करता हूँ अराउंड 50% ऑफ योर सब्जेक्ट्स इन सिविल इंजीनियरिंग। And this is our official Telegram channel, my dear friends, and we do have lot many, as you know, free content available on special classes as well as on Unacademy official YouTube channel. But still, we recommend our learners to go for our Plus and Iconic plan. The reason being, in Plus you can have access to live classes on the daily basis. Weekly tests are there, structured courses are there, crash courses are there, rank improvement batches are there, and you guys can also unlimited access to the content. And if I'm talking about the iconic one, which is the superset of Plus, where you are going to get all the benefits of Plus. Apart from that, also you're going to get a personal coach who is going to plan your study, who's going to keep the booster session for you, who's going to analyze your test at the personalized level. Not only this, also you're going to get the specialized notes and practice sets along with the dedicated doubt clearing educator. So whether it is a matter of Plus or iconic, feel free to use the code AISH10. Dear, all these are the prices of an Unacademy subscription, and for instant 20% off, you guys can use AISH10. This model is available from 3 months to 2 years, and Plus is available from 6 months to 2 years. And by default, the discount is 10%. But if you are planning your subscription till tomorrow, then you can unlock 20%. Dear, these are the information on the upcoming batches or recently launched batches, and in the recently launched batch Evolve and Ascend, we have started strength of material. And once again, welcome you all guys in the marathon session. It is the 4th session, and agenda in this session is to cover combined stress, spring, shear center, column, deflection of beam. Pressure vessel I'm not going to take now because it is not a part of your GATE syllabus as per the revised format. So combined stresses is springs, shear center, column and deflection. And जो order मैं use करने वाला हूँ, that is first I will be taking column. Immediately after that I will be switching to combined stresses, then shear center and spring, and last I will be giving to the deflection of beam. So nearly 50% of the time I would like to spend in these topic number 1, 2, 3, 4, not even 50%, 40% of the time I would like to spend on these 4 topics, and deflection of beam I am going to take at the end, okay, because this is required more time and all. Okay, तो start करते हैं without wasting the time. एक बार session को dear share कर दीजिए सब लोग, please share your session dear, all of you. Okay, just a minute, I am sharing it. ओके, सो स्टार्ट करते हैं. सीक्वेंस मैंने आपको समझा दिया. कॉलम, देन कंबाइंड स्ट्रेसेस, देन shear सेंटर, देन स्प्रिंग्स, देन डिफ्लेक्शन ऑफ बीम्स. Pressure vessel we are not covering as it is not going to come in your GATE 2022. Okay, so let's start. I hope you all are familiar with the word column. What is column? You all know. Whenever the word column is there, the very first thing which came into our mind, which comes into our mind, that they are axially loaded member. They are axially loaded member. So there are much category of axially loaded member. We do have pedestal, we do have strut, we do have post, we do have stanchions, we do have booms. So all these are the various categories of axially loaded member, or you can say of column. Okay, so all these are the axially loaded member here for you. And whenever we are designing the column, we have to make sure that the strength of the material is greater than the axial load or the maximum stress developed on your section. Okay, so after this I would like to draw your attention towards the type of equilibrium which one has usually. So total types of equilibrium, there are 3 types of equilibrium. 3 types of equilibrium. So you all are familiar with it. You also use this concept in mechanics as well as in your fluid mechanics. What is stable equilibrium, unstable equilibrium and neutral equilibrium. Stable equilibrium class 11 से पढ़ना चालू कर देते हो. This is the case of potential. This is the case of stable equilibrium where the potential energy of the system is already least, so it is the most stable condition. Second type of equilibrium which you can see is unstable equilibrium where the object is at maximum potential energy, and third is your neutral equilibrium where potential energy is the same at all the positions. Stable equilibrium is stable because even if you are going to disturb this ball, even or any system by a small amount, it is not going to create a problem for you. After some time it will again come back to the original position, like your spring mass system, like your pendulum and all. Unstable equilibrium is there that this object is there at the verge of failure. So the moment you are going to touch it, it is this object is never going to come back to its original position. This is unstable equilibrium. So this is stable equilibrium, this is unstable equilibrium, and neutral equilibrium is this. Here also the particle is in equilibrium, but if you are going to disturb it, it will come to its revised position, but there also it will maintain its equilibrium. It is your neutral equilibrium. So in design of column, in the analysis of column, the thing which we have to take care in our mind is stable equilibrium. So based on that you might need to do several calculation for calculating critical load. For example, suppose if this is your simplest of simplest beam, okay, let's suppose it is the simplest of simpler column, not beam. it is attached to, let's suppose, some spring. Spring का introduction भी दूंगा अभी. And suppose if you are applied here any load P, so if the stiffness of this spring is K, now what is the critical load when it is going to fail? It will be failing when there would be some generation of overturning moment. So overturning moment here is how much? Overturning moment is equal to, on its deformation, it may be like this, or vice versa can also be the case. Okay, so this is the revised position of P now. Let's say this displacement with respect to its mean position is x. So you can say delta. You can say that this overturning moment is nothing but P into delta. Now what is the resistant moment if length of this column is L? Now what is the resistant moment due to this lateral confinement due to this spring? So resisting moment here would be what is the force generated here? If you are going to draw the free body diagram of this spring, then spring will look like this. Spring will look like this. So here the force generated would be F into delta, okay, or K into delta, sorry. So same K into delta would be acting here. So resisting moment would be force into displacement into lever arm. Lever arm is L. So for stable equilibrium, overturning, so P delta is equal to K delta L. So delta and delta will cancel. From here you can calculate the critical load, and this critical load is equal to K into L. As long as your load would be less than K into L, so you would be safe. Okay, you would be safe. Similarly, you can repeat this exercise for multiple springs restrained at same level as well as at multiple level. Okay, so after this, dear, we would be dealing with the various theory of failure. Theory of failure of column. What are the various theories of column? Generally we use two. First one is Rankine theory. Oh sorry, first one order wise chalte hain. Euler's theory we will be seeing, and second one is Rankine theory. So both of this theory we have to study here. Okay. So what are the various assumptions involved in the Euler's theory? What is Euler theory? Okay, I will explain. And what are the assumptions in the Euler theory? So first of all, give the heading Euler's theory. So assumptions involved in the Euler's theory are assumptions. तो पहले assumption लिख लेते हैं, फिर डिटेल में समझाता हूँ क्या है. First assumption is that material is isotropic, homogeneous, and linearly elastic. In which Hooke's law is valid. In which Hooke's law is valid. Second assumption, as I told you, the BTEC assumption, plane section before application of load will remain plane even after application of load. Okay, so third assumption is, which is very very critical, and it is also a cause of limitation in Euler theory, that here the failure is considered due to of long column, and means here failure will be due to the buckling. So you can say that column under analysis is assumed to be एज्यूम टू बी लॉन्ग कॉलम। लॉन्ग कॉलम का एक ही मतलब है, बस लॉन्ग कॉलम का एक ही मतलब है कि फेलियर जो होगा यहाँ पे वो इट इज ड्यू टू दी buckling, not due to the crushing. Okay, this is the limitation of Euler theory. That's why Rankine theory came, which have taken care of crushing short column as well as long column. But Euler's theory is only valid for long column. Okay, which is having higher value of slenderness ratio. Okay, so third assumption means failure is due to buckling only. Okay, so this theory is only for long column. Are you getting the point or not? Okay, and one more assumption is there, which is a common sense thing. Before the application of load, the column was perfectly straight. Okay, initially column is straight, मतलब लाइन ऑफ एक्शन इसका एकदम मेंटेन रहेगा. That is before application of load. ओके, सूरज जी कह रहे हैं सर एसएससी जेई में नॉन टेक की तैयारी कैसे करें, कोई बुक बताएं सर प्लीज. सूरज जी मैं कहूँगा कि यू कैन सब्सक्राइब टू आवर एसएससी जेई चैनल, वहाँ पे आपको प्रॉपर गाइडेंस मिलेगी. Okay, Unacademy SSC JE channel is there, so please try to go in that channel and वहाँ पे आपको educators appropriate guidance दे देंगे, because I do not have much idea about non technical things. Okay, चलिए डियर आगे बढ़ें. क्या आगे बढ़ें? अब यूलर थ्योरी बोल क्या रही है? देखो यूलर थ्योरी क्या बोल रही है वो तो मैं आपको यहाँ बता दिया. यूलर थ्योरी इज सेइंग दैट crippling load or critical load, okay, yeah, neutral load, whatever is this, this is defined by n square pi square ei upon l square. N square pi square ei upon l square, where n is the number of buckling loop, I is the minimum moment of inertia about the transverse axis, l is the effective length of the column. PCR is also known as buckling load, it is known as critical load, इसको यूलर लोड भी बोलते हैं, न्यूट्रल लोड भी बोलते हैं, क्रिपलिंग लोड भी बोलते हैं. तो ये सारे नाम होते हैं हमारे किसके? PCR के, है ना. n क्या है? नंबर ऑफ बकलिंग लूप. Like in this case there is only one buckling loop, nodal distance 1. Here you can see there are 2 cycles are there, so here n you have to take 2, and here 3 cycles are there, so n you have to take 3. Okay, so this is the value of n, and I is the moment of inertia of this column section about the transverse axis, and there are 2 possibilities while taking I. Let's suppose this is your cross section of column. Let's suppose this is your one axis. Let's suppose this is your another axis. So here you can see that which cross section you can take, moment of inertia about which. So this is one case, this is another case. So whatever is the least moment of inertia that we have to consider, in this case. Okay, so that's why it is written minimum moment of inertia about the transverse axis. Minimum moment of inertia about the transverse axis. Okay, now dear, how we can obtain this expression, इसका थोड़ा सा आइडिया मैं आपको दे देता हूँ. Let's suppose I do have a column here. This is column. Let's say its length is L, and I have applied a load P here. Okay, so due to this buckling may happen, and if I am going to take bending moment at any section, let's suppose this distance I am taking y, because normally in slope and deflection we will be studying that across we will be taking y, along the axis we will be taking x. तो रिजल्ट्स आपको थोड़े यूज करने में आसान होंगे. सो दिस इज y डियर and this is x. So if I am going to draw the free body diagram here, then it is going to have some moment m. This is the load P, this distance is x, this distance is y. So if I want to write m value, then m value is nothing but it is minus p into y, Hawking bending moment, minus p into y, because this is also p na, p into y. Okay, so if I am using the double integration equation, which we will be seeing soon, so which is ei d2y by dx2 is equal to m. So m is equal to minus py. So I can write here that d2y upon dx2 plus py upon ei is equal to 0. So this is the mathematical differential equation of second order. So you can write d2y upon dx2 plus try to write it like this, under root of p upon ei square into y is equal to 0. Now on solving this equation, dear, what you can do, the general equation of the general solution of this equation, okay, it is also equation of simple harmonic motion ना, जैसे आप f is equal to minus kx लिखते हो, so d2 a upon dx2 d2y upon dx2 dt2 upon k by m. So it also, it is m into a plus k into x is equal to 0. Okay, so d2y upon dx2 plus k by m into x is equal to 0. So this is also resembling with this equation. Okay, so similarly, if you are going to make the solution of this equation, then y is coming out to be c1 cos x under root p upon ei plus c2 sin x under root p upon ei. So if I am applying the boundary condition like at x is equal to 0, y is equal to 0, and at x is equal to L, y is equal to 0. So at x is equal to 0, this is 1, this is 0, y is equal to 0, so c1 is coming out to be 0. At x is equal to 0, y is equal to 0, from that c1 is coming out to be 0. And at x is equal to L, if I am keeping y is equal to 0, then I am going to get what? Sin L x under root p upon ei equals to 0. Okay, because c2 cannot be equal to 0, otherwise solution will vanish. So this is the condition from second boundary condition. At x is equal to L, y is also equal to 0. Now the general solution of sin theta is equal to 0 is theta is equal to n pi, and okay, n pi होगा ना, sin 0 पे भी 0 होता है, 180 पे भी 0 होता है, और 360 पे भी 0 होता है, so n multiple of 180 degree. So if you are going to square, so it is L square p upon ei is equal to n square pi square. So p is coming out to be n square pi square ei upon L square. So this is what I think we have written here, n square pi square ei upon L square. So like that, by using the double differential equation, we would be using, we will be able to calculate the value of critical load, where n is the number of buckling loop, and pi, you know, ei is flexural rigidity, L is length of the column. L is known as the length of the column. Okay, are you getting the thing or not? So that's like this we can derive the equation. Okay, generally if we are keeping for n is equal to 1 for one loop, the distance between two zero moment is also known as L tends to L effective. So we can also write PCR is equal to pi square ei upon L effective square. Okay, are you getting the thing or not? Tell me, are you all getting the thing or not? Okay, so now PCR is equal to pi square E. What is I? I is area into R minimum square upon L effective square. So PCR can also be written as pi square E area upon L effective upon R का whole square. R is कौन सा वाला? Minimum radius of gyration, and L effective upon R, you all know it is known as the slenderness ratio. It is known as the slenderness ratio. So pi square E area upon lambda square. where lambda is slenderness ratio. Okay, so now if PCR upon area can be written as pi square E upon lambda square, and PCR upon area is known as the critical stress or buckling stress. So this is also the very common expression which we use in the analysis of column. I hope it is clear to you here. Okay, so this is where sigma CR is buckling stress. It is buckling stress. Okay, and here L effective we have taken, and I hope you all know what is L effective. L effective is the distance between two zero moments. Let me write it. Okay, so or you can also say it is the distance between consecutive contraflexors, or you can also say it is the distance between the two continuous contraflexors. Okay, now my dear friend, for calculation, very good afternoon dear Daksh. Now for calculating L effective, we have some different condition. So let me revise you quickly. If we have pin end connection, now tell me what is the L effective. Suppose this is the L, so here L effective is equal to L only. Okay, similarly if we have one end fixed and one end is pinned, so we have L effective as L by root 2. Okay, so all these are the solutions of Euler buckling theorem. Okay, if both the ends are fixed, these four cases are very widely used, then L effective is L by 2. If we have one end fixed and one end as free, then L effective you can take as 2L. So please remember at least these four cases L effective. Hinge, it is L only. Okay, because you can see the entire length is involved in developing two consecutive contraflexor for one node. And here if you are going to draw the deflected pattern, you are going to draw the Bmd, then you will be getting it like this. So you can see that effectiveness has been reduced. It is now this much. Okay, and similarly अगर आप यहाँ पे BMD draw करोगे, deflected pattern draw करोगे, then again the length remains almost half. But here if you are going to draw, then you will be needing double of the distance. So that's why L effective here is 2L. Okay, I hope you are getting the point solved. Any doubt to anyone? Little lag issue. Let me check. रुषि लैग इशू मेरे एंड से तो नहीं है यार, सॉफ्टवेयर इज वर्किंग परफेक्टली फाइन, नो लैग इट इज गिविंग. मतलब जो स्ट्रीमिंग लैग है वही आ रहा है जो होता है 3 से 4 सेकंड का, उसके अलावा और कोई लैग नहीं है. डाटा रेट इज ओके. ओके, व्हाट इज द डिफरेंस बिटवीन रिस्ट्रेन्ड एंड ट्रांसलेशन? Dear, restrain is a general thing. Translation is one particular dimension. Restrain means if somebody is restrained, it can be restrained about rotation, it can be restrained about axial deformation, it can be restrained about translation. Whereas the translation is only one dimension of that. Translation is only one dimension of that. But restraining can be done along the translation, along the shear, as well as along the rotation. Are you getting the difference, dear Daksh? Are you getting the difference, dear Daksh? Okay. So anything else? Anything else? Okay. Now if I ask you what all are the limitation of this theory, then who will be able to tell me? What all are the limitation of this theory? Euler theory, in the assumption only I have mentioned, in the assumptions only I have mentioned that it is for long column. It is for long column. Means here they have taken the failure due to buckling only. If failure is due to buckling, means it is for long column only. So this is the very first limitation of Euler's theory. Let me write it. First one is it is not valid for short column. It is not valid of short column because it is the prime reason of failure is buckling only. आपने देखा होगा ना जब हमने इसको derive किया, so we have created a bending moment here, and bending moment is only there if this column is about to buckle. If bending is there, in column bending is only possible if it is subjected to some buckling force and all. Okay. So first limitation is it is valid for, it is not valid for theory, or let me write Euler theory not applicable for short column. It is not applicable for short column. Okay, ठीक है. Yes, वही मतलब axial stress is not taken into account, मतलब short column. Okay. Whereas why it is a limitation? While in short column crushing happens before buckling. तो वहां पे तो फेल हो गया ना बिफोर बकलिंग. ठीक है. आर यू गेटिंग दिस थिंग और नॉट? ओके. सो इफ somebody ask you what is the minimum slenderness ratio, so that Euler theories can be applied. अगर मैं आपसे पूछूं कि वो कौन सा मिनिमम स्लेंडरनेस रेशियो है जिसके ऊपर आप यूलर थ्योरी लगा सकते हो, तो आप निकाल सकते हो. आई थिंक मैंने आपको बता दिया है. डायरेक्टली नहीं बताया, इनडायरेक्टली बताया है. कैसे? We have seen this. Sigma CR is pi square E upon lambda square. Sigma CR is pi square E upon lambda square. What is lambda square? Lambda square is pi square E upon sigma CR. So lambda is pi under root E by sigma. And this sigma, the E and sigma, they are the function of your material. Okay, so most common material we are using is steel. So steel की अगर मैं आपसे बात करूं डियर, स्टील की बात करूं, then what is the value of lambda? It is lambda value is pi under root Young's modulus for steel is 2 into 10 to the power 5, and if I am considering the mild steel, sigma can be taken as 250 MPa. So tell me what is the value of lambda coming out? What is the value of lambda is coming out? Tell me. कैलकुलेटर नहीं है मेरे पास, जरा बताइए. आप लोग कैलकुलेट करके जरा बताइए जल्दी से फास्ट. Yes, it is coming out to be 88.8. 88.8. Yes. Okay, good, Rushi. So 88.8. So generally lambda for steel is 88.8. For aluminium it can be different. For copper it can be different. So lambda is the property based on the strength of the material. Okay. Okay. ठीक है, तो स्टील यूज करते हैं फॉर स्टील. फॉर स्टील. ठीक है, चलिए. So you can keep a note here that Euler's theory is applicable in steel for lambda greater than 88.8. If lambda is less than 88.8, then it is a short column. It is a short steel column. Okay. So mostly एक ग्राफ बनाया जाता है, mostly एक ग्राफ ड्रॉ किया जाता है. ग्राफ क्या है? ये क्या कर दिया? एक मिनट हो जाइए, थोड़ा सा ऑर्डर चेंज हो गया. ओके. हाँ, सो यूलर ग्राफ फॉर नॉन. यार एक तो पता नहीं आप लोग कंक्लूजन कहां से निकाल लेते हो. दक्ष, आई डू नॉट नो. व्हेन डिड आई से इट इज ओनली एप्लीकेबल फॉर स्टील? Have I ever said that it is applicable for steel? I am saying if you want to apply Euler's theory for steel, then make sure its slenderness ratio is greater than 88.8. Okay, because if lambda is less than 88.8, it is going to be a short column, and in short column crushing happens before buckling. In short column crushing happens before buckling. You can apply Euler's theory for any homogeneous and isotropic material. Okay, you can apply it for aluminium, copper. Okay. Yes, E is applicable for no. Rushikesh, we can also not comment based on E only, because concrete is also there. You cannot apply theory for concrete. You will not be able to apply theory for concrete. That is the reason why IS code 4562,000 has given different effective lengths. बात समझ में आ रही कि नहीं आ रही है? तो ये जो assumption हम लिखते हैं ना, इसका बहुत बड़ा इंपॉर्टेंस होता है. अगर ये सिर्फ स्टील के लिए होती तो मैं लिख देता assumption में ही only for steel. Okay, so isotropic, homogeneous and linearly elastic. So concrete के लिए आप नहीं लगा सकते इसको. But aluminium, steel, copper, they all are isotropic, homogeneous and linearly elastic. In all material where Hooke's law is valid, under working stress you can apply Euler's theory. Okay. Is it clear, Daksh? Daksh, clear है? So that is the case. Now Euler failure graph. Euler failure graph. This is y-axis, this is x-axis, this is y-axis, this is x-axis. This is your range of short column. Then you would be getting intermediate column. Then it is varying hyperbolically for long column zone. It is hyperbola. Okay, so if okay, so this you can apply. So I, just to make you understand, I have to take several points within this graph, है ना, कुछ points लेने हैं इस graph के अंदर. Let me take that. So these points are, let's say this is point number A, let's say this is point number B, okay, this is point number C, and this is point number D, this is point number E, and also let me bifurcate it somewhere here. So this up to green, the area is of a short column. From green to blue, it is intermediate column. Intermediate column. Here we cannot comment that filling is due to which kind of load. And this is the case of long column. This is the case of long column. Okay. If I am talking about point number A here, now listen to me very, very carefully. If I am talking about point number A, then this A point is lying in the short column zone, but the value of stress which A is going to experience is higher than the critical value. So this A point, this A at this A stress, my short column is going to fail. So I can say here A is giving you a point, okay, where column is short, where column is short, and it is unsafe, and it is unsafe in unsafe. If I am talking about point number B, if I am talking about point number B, then again I can say that column is short, but it is safe. Column is short, but it is safe. हाँ यार, वो बच्चे हैं जो आवाज कर रहे हैं. कोई बात नहीं, आपके साथ भी होगा. बेबी इज लिसनिंग वेरी केयरफुली. बस तुम ही लोग नालायक हो, तुम ही नहीं सुनते हो. चलो ठीक है. ओके. If I am talking about C point, if I am talking about C point, then what will happen? Here the failure is due to the intermediate column. But yes, still C point is within this graph. Still this C point is within graph. It is again safe. So here column is intermediate. Column is intermediate and safe, and it is safe. Okay. What about D, dear? What about D? What about D? D is a long column. D is long column and safe column. D is long column and safe column. And E is long but unsafe column. मैं दिखाई दे रहा हूँ. चलो इधर लिख देता हूँ E. E point is long but unsafe column, but it is unsafe. Okay. Clear है कि नहीं है? अरे बात समझ में आ रही है कि नहीं आ रही? Are you getting the point or not? Tell me, guys. ठीक है. Now this is all about Euler's theory. This is all about Euler's theory. Okay. So crippling lower expression I have derived for you. Assumptions I have written for you. Okay. So different, based on the different end condition, I have also given you the effective length. Limitations I have also explained, and when we can use it for particular material I have discussed, and I have discussed specifically for mild steel. This is the Euler's failure graph. Okay. Now to overcome this problem, we do have Rankine theory. To overcome this problem, we do have Rankine theory. Rankine theory take care of short column as well as long column. So first of all, applicable for long and short column both. Okay. And it means, that is, it assumes the mode of failure it assumes the mode of failure as crushing and buckling both. It assumes the mode of failure as crushing and buckling both. Are you getting the point or not? Tell me. Okay, here the Rankine crippling load is given by Rankine failure load या crippling load is given by anybody, किसी को आइडिया है? Is given by actually weighted average लिया जाता है, सॉरी क्या बोलते हैं इसको, हार्मोनिक एवरेज 1/p is equal to 1/pc plus 1/pe, where pc is due to crushing and pe is your Euler load. तो रैंकाइन थ्योरी ने क्या किया? रैंकाइन थ्योरी ने सिंपली यूलर थ्योरी के साथ अपने क्रशिंग वैल्यू को मर्ज कर दिया और उन दोनों का इनवर्स एवरेज ले लिया. सो लाइक दैट ही हैज कैलकुलेटेड द रैंकाइन क्रिपलिंग लोड. ओके, सो आर यू गेटिंग द थिंग और नॉट? सो p 1/p is equal to 1/pc plus 1/pe. Here this p is Rankine failure load. This is Rankine failure load. PC is crippling load, sorry, crushing load, and P उनको भी पूरी इज्जत मिली जाएगी भाई, पहला काम तो यूलर ने किया था. इट इज यूलर्स बकलिंग लोड और यूलर्स लोड. ओके, सो 1/pc प्लस 1/p दोनों को तवज्जो देते हुए रैंकाइन ने बस अपना सिंपल सा वेटेड एवरेज लिया और काम कर डाला. आर यू गेटिंग द पॉइंट और नॉट? सो दिस P कैन ऑल्सो बी रिटन एज प्रोडक्ट बाय सम. जैसे रेसिस्टेंस का पैरेलल कनेक्शन होता है वही तो है, प्रोडक्ट बाय सम, PC इंटू PE अपॉन PC प्लस PE. कोई डाउट किसी को यहां तक? और इट कैन ऑल्सो बी रिटन एज इट इज योर PC डिवाइडेड बाय 1 प्लस PC ओवर PE. दिस इज योर रैंकाइन फेलियर लोड. Okay, if PC can be written as sigma c into area, 1 upon, it is written as sigma c into area. What is PE? What is PE? How we can write PE dear? It is pi square E I upon कितना ले लेते हैं हम? L square into L effective square. Okay, like that we can do. And I can be written as area into R square. I can be written as area into R minimum square. Area and area can get cancelled. So from here P is coming out to be sigma C into area divided by 1 plus sigma C. L upon R is lambda square upon pi square into E. So this is the expression for calculating Rankine's failure load. And if you want to work in terms of Rankine failure stress, then P upon A is again Rankine stress. So P upon A is Rankine stress and it is equal to crushing stress upon 1 plus lambda square sigma C upon pi square E. Rankine stress. Okay, Rankine failure stress. So these are the important formulas which you can calculate. Are you getting the point or not? Tell me. So sigma c, pi and E are constant for a particular material. So we can also say that the C is sigma c over 1 plus alpha lambda square, where alpha depends from material to material. For steel it can be different. For cast iron it can be different, for timber it can be different, for wood it can be different. So generally alpha is 1 upon 75,000 or 7,500 for mild steel. It is 1 by 1600 for cast iron, and it is 1 by 750 for timber. It is 1 by 750 for timber. ठीक है, चलो ठीक है, जबरदस्त एक्सप्लेनेशन. हाँ बस यही है, आवाज़ तेज कर दो तो आपको लगता है एक्सप्लेनेशन अच्छा हो गया. यही मैं धीरे धीरे बोलता तो बोलते हो कि सर मज़ा नहीं आया। ठीक है, तो डियर ये है आपका पूरा का पूरा फंडा, और इस रैंकाइन थ्योरी ने अपने आप ही काम कर दिया पूरा, किसका, शॉर्ट कॉलम का भी और लॉन्ग कॉलम का भी। सो दिस इज द कंसेप्ट हियर, बेसिकली दिस इज द कंसेप्ट। आर यू गेटिंग द पॉइंट और नॉट? टेल मी। कोई डाउट किसी को यहाँ तक है तो बता दीजिए, फिर बढ़ते हैं आगे। तो यूलर और रैंकाइन पूरे हो गए। रैंकाइन में ज्यादा कुछ नहीं है, बस उसने कुछ नहीं किया, उसने वेटेड एवरेज ले लिया क्रशिंग और यूलर दोनों का, और बस कर दिया अपना काम आगे। ठीक है, ठीक है, कोई डाउट हो तो बताइए, फिर बढ़ते हैं नेक्स्ट स्टेज पे इसके। चलो, सो नो डाउट आई एम एक्सपेक्टिंग। नाउ नेक्स्ट इज विच इज अगेन वेरी वेरी इंपॉर्टेंट। इसको आप कॉलम के अंदर भी कर सकते हो, इसको कॉलम के विदाउट भी पढ़ सकते हो। दिस कंसेप्ट विल बी वेरी वेरी यूजफुल इन योर कॉलम्स, इन योर प्री स्ट्रेस कॉन्क्रीट, इन योर कंबाइंड स्ट्रेसेस थ्योरीज। ओके, ठीक है। CPMT क्या होता है? ठीक है, चलो अब कंबाइंड स्ट्रेस को थोड़ा समझते हैं। व्हाट डू यू अंडरस्टैंड बाय कंबाइंड स्ट्रेसेस? एक चीज तो कॉमन है कंबाइंड स्ट्रेसेस के अंदर कि यहाँ पे एक से ज्यादा स्ट्रेस फंक्शन लग रहे होंगे और उनके कारण आपको स्ट्रेसेस डेवलप हो रहे होंगे। अल्टीमेटली यू हैव टू टेक द एडिशन और सब्सट्रैक्शन और रिजल्टेंट ऑफ ऑल दोज स्ट्रेसेस। ओके, क्लियर है कि नहीं है? कंप्लीट करा दो आज ऑल टॉपिक, कंप्लीट करा दो आज ऑल टॉपिक। हाँ, सारे टॉपिक कंप्लीट ही कराऊंगा डियर। सोम के सारे टॉपिक कवर कराऊंगा। एक बोल दिया मैंने, प्रेशर वेसल स्किप करवा रहा हूं क्योंकि प्रेशर वेसल क्या है, आपके गेट में नहीं आ रहा। ठीक है, चलिए तो कंबाइंड स्ट्रेसेस पे बात करते हैं। इफ योर कॉलम और एनी मेंबर इज सब्जेक्टेड टू एक्सियल फोर्स and that force is acting at the CG of your member, then due to that compressive stresses will be generated. Due to that compressive stresses will be generated. थोड़ा सा विजुलाइज करना पड़ेगा इसके अंदर, बट कंसेप्ट्स आर वेरी ब्यूटीफुल हियर। मान लीजिए कि ये मेरे पास एक एक्स एक्सिस है, ये मेरे पास एक वाई एक्सिस है, and if my load is acting over this intersection, maybe like this, so this is P, and let's suppose this column is fixed at base, और यहाँ पे इसका एरिया जो है let's suppose that is A. Now what will are the stresses? What will are the stresses here dear? The entire stress is due to the compressive stress, और यहाँ पे compressive stress कितना लग रहा है डियर? यहाँ पे compressive stress कितना लग रहा है? It is P upon area. It is P upon area. So यहाँ पे only one stress is acting, and that stress is normal stress or axial stress, that is P upon area. Okay, ये तो सब कर लेते हो, ये तो आप सब कर लेते हो। Let's suppose this is your x axis. Let's suppose this is your y axis. इसको x मान लो, इसको y मान लो। अच्छा, मजा तब है जब इस लोड को मैं इधर उधर भटकाऊंगा। मजा तब है जब, यस डियर शांति, मजा तब है जब इस लोड को मैं इधर उधर भटकाऊंगा। फॉर एग्जाम्पल मैं इस लोड को लेके चला गया, लेट्स सपोज यहां से हटा करके, यहां से हटा दिया मैंने इस लोड को। ओके, अब इस लोड को मैं लगा रहा हूं कहीं यहीं, एंड लेट्स सपोज दिस डिस्टेंस is लेट्स सपोज दिस डिस्टेंस इज, कितना ले लो, E ले लो इस, या इट इज द एसेंट्रिसिटी अबाउट x एक्सिस, so it is E ई ले लो, ठीक है। इसको देखो कई बुक्स में EX भी लिखते हैं, कई लोग इसको EY भी बताते हैं, ठीक है। इट इज अबाउट X एक्सिस बट इट इज अलोंग द Y एक्सिस, सो आई एम राइटिंग इट EY. I am writing it EY. So don't be confused. So now if this P is shifted from centroid, and let's suppose there are 4 corners P, PQRS से यूज हो गया, A यहाँ पे लगा दिया मैंने. So अल्फा बीटा गामा डेल्टा कर लो, अल्फा बीटा गामा एंड डेल्टा. लेट सपोज मेरे पास 4 कॉर्नर है, अल्फा बीटा गामा डेल्टा, ठीक है. सो कैन यू टेल मी व्हाट आर द स्ट्रेसेस डेवलप्ड एट अल्फा एंड बीटा कॉर्नर्स? लेट सपोज द विड्थ ऑफ दिस कॉलम इज B, and let's suppose this is the depth of the column, or you can say cross section. This is B and this is D. Or consider 1 to be L. Okay, let's say this is L of the column, this is width of the column. So tell me what all are the stresses developed at A? What all are the stresses developed at A? Now at A, P by A would be happen. It will be occurring. अगर मैं इसका प्लान बनाऊं तो ये प्लान अगर आप देखोगे डियर, तो ये प्लान आपको दिखेगा कि I can convert this load now like this. I am shifting this P at center. I am shifting this P at center. This is P. And apart from this, movement will also be generated about X axis. So about X axis, movement will also be generated. So that movement is going to be P into EY. P into EY, and P into EY is the moment generated about X axis. P into EY is the moment generated about X axis. Okay, so are you getting the point or not? ठीक है. PQRS नहीं हो सकता, अल्फा बीटा गामा डेल्टा, मजा सा नहीं आ रहा अल्फा बीटा गामा डेल्टा में. CDEF नहीं हो सकता. IJKL ले लो यार, I भी मोमेंट ऑफ इनर्शिया होता है. क्या लोगे? एक काम करो ना, जरूरी थोड़ा ना, कसम थोड़ा का रखिए, अंग्रेजी यूज करनी है. 1 2 3 4 ले लो, 1 2 3 4, ठीक है. नाउ व्हाट इज द स्ट्रेसेस एट 1? व्हाट इज द स्ट्रेसेस एट 1? स्ट्रेसेस एट 1 वुड बी P अपॉन एरिया. ओके, बट नाउ 1 and 2 fibers, in fact the line joining 1 and 2 is the line which will be experiencing the compressive stresses in addition to P by A. You know why? Because due to P into EY, the side which is far from me, in that side compression will be happening, and towards me side, from access to me, there would be some tensile stresses developed, because when bending would happen, we have seen in the bending stresses about neutral axis bending is going to happen. So since MX is there, so rotation of the cross section will also happen about X axis. So one axis will be subjected to compression, and another side there would be tension. Okay, so due to MX, what would happen at 1 and 2? Compressive normal stresses will be developed. Due to MX, what will happen at 3 and 4? Tensile bending normal stresses will be developed. So whenever I am calculating the net stresses or combined stresses, then at 1 and 2 the stresses would be increased, at 3 and 4 the stresses would be decreased. Okay, so if I am calculating M1, it is sigma P by area plus M upon I into Y. What is Y? Y is B by 2, because I have to take maximum at one location. And same is the case with M2. So at M1 and M2, okay, sigma 2, and same is the case with sigma 1. So net sigma 1 and sigma 2 are direct sigma plus sigma due to bending. Similarly, if I want to calculate sigma at 3 or sigma at 4, then it will be P by area. It will be compressive in nature for all the section. This P will be compressive for each and every fiber, but minus PEY upon I into B by 2. sigma 3 and sigma 4, here the tensile stresses would be less. Here the compressive stresses would be less, because due to the indirect action of movement, this zone is in tension. So overall, the section may have compression or tension, or it may have zero stresses depending upon the magnitude. So tell me. Okay. So ऋषिकेश की बात मान लेते हैं, रोमन नंबर ले लो. ओके, रोमन नंबर ले लो, अच्छा आइडिया है, गुड. ओके, tell me, any doubt to anyone? Any doubt to anyone so far? Any doubt to anyone? Tell me very clearly. So sigma 1, sigma 2, sigma 3, sigma 4, we can calculate. Okay. But again, my dear friend, here I have taken eccentricity only about one axis. Here I have taken eccentricity only about one axis. It may also happen that you might have eccentricity about both the axes. Okay. Let me give you an example. Okay. So let me draw this diagram again, dear. So understand the respective things by your own, that it is going to be fixed and all. Okay. So I am only focusing on the cross section, dear. Okay. Now tell me what would happen. This is going to be the EY. This is going to be the EY. This is going to be the EX. This is going to be the EX. So this is EX. This is EY. Okay. So what would happen now? Don't you think it is going to have a biaxial bending along with the axial stresses? It is going to have biaxial bending along with the axial stresses, because this time the bending moment is being developed about x-axis, whose value is what? P into EY, and the bending moment is also developed about y-axis, whose value is P into EX. So this time the case is subjected to biaxial bending along with the axial loading. So this time the total stress component will be due to three actions. One is due to direct action of P, and another two due to the indirect action of P, which is nothing but moments. Okay. So if I am calculating stress in fiber number 1 in corner number 1, then it is P upon area. Okay, let me simplify it and draw it in a simpler manner. So your revised cross section may look like this. Your revised loading pattern may look like this. This is so P I am going to shift at the center, but along with this P, one moment will be there about y-axis, it is P into EX. One moment will be there about x-axis, which is P into EY. So try to see the consequences independently. Try to see the consequences independently. Due to load P, due to the center P, it is P upon area. So now I want you guys to answer. What would happen due to PEX and what would happen due to PEY? Please let me know. ज़्यादा ना लो भाई, पानी सेहत के लिए अच्छा होता है। देखो 1 2 3 4 सभी में अगर मैं देखूं, इन सेक्शन 1, इन सेक्शन कॉर्नर 2, इन कॉर्नर 3 as well as in corner 4, so one thing is there that it is P by A is going to happen everywhere. P by A is going to happen everywhere. Now पहले mx को डील कर लेते हैं। mx को, mx आपको पता है कि 1 और 2 पे पॉजिटिव स्ट्रेस डालेगा एंड 3 एंड 4 पे नेगेटिव स्ट्रेस डालेगा। तो mx देखोगे, एक एक करके लकड़ी तोड़ेंगे। जब लकड़ी को गुच्छा होता है, व्हाट वी यूज्ड टू डू, वी यूज्ड टू टेक देम इंडिविजुअली। प्लस 1 पे यू कैन सी 1 and 2 side would be in compression and 3 and 4 side would be in tension. So due to which what would happen, additional compressive stresses will be developed at these two corners. So this is P into EY, which is moment about x-axis, upon I. What is I? It is LB cube by 12 into Y. Y is what? Y max, and this is equal to B by 2. Similarly, 2 portion will also having positive stress due to bending, and 3 and 4, like we did earlier, they are going to have negative stress due to bending or tensile stress due to bending, but their magnitude would be same. Their magnitude will be same. Okay. Next thing is, now we have to tackle moment about y-axis. So moment about y-axis is PEX. What will happen due to this moment about y-axis? Fiber 2 and fiber 3 would be in compression, but fiber 1 and fiber 4 would be in tension. Are you agreeing to me or not? First of all, tell me. Are you agreeing to me or not? First of all, tell me. Fiber 2 and 3 are in compression and 1 and 4 are in tension. Tell me. Okay. Okay. So 2 and 3 plus M upon I. Although this I and blue I and red I are different. Blue I is about blue axis, x axis. This red I is about y axis. Okay. Into L by 2, because I have already told you this is L and this is B. Okay. So this is going to be how much? This is going to be L by 2. But it is negative, not positive, because fiber 1 is going to have tensile stress due to this. But yes, this one is 2 is positive. This one is positive. 3 is also positive. 3 is also positive. But 4 1 is okay. Yes, I am taking compression as positive in this case. I am taking compression as positive. Okay, because in column the primary load is compression only. Okay, so we are taking compression positive in this here. We can even write here compression. Here I will be taking positive. ओके चलो, ये हो गया सिग्मा 3 एंड सिग्मा 4. इज इट क्लियर? So this is how we can find the direct combined stresses due to different orientation of load. Okay, and this blue वाला I जो होगा वो होगा आपका LB cube by 12 and जो लाल वाला I होगा वो आपका होगा BL cube upon 12. It is BL cube by 12. Okay, don't be confused here. And here we have used only moment of inertia about x-axis. So here I is common, same. I is LB cube by 12 only. Okay, is it clear? Okay, so that is the case. That is the case. ठीक है. So ये हो गया हमारा x और ये हो गया हमारे पास y. So this is all about combined stresses. We can make several observations out of here. Okay, we can make several observations out of here, and you know, you might have heard of middle 1/3 rule. For uniaxial loading, suppose if this is my column, let's suppose this is L and this is B and this is your x-axis, this is your y-axis, and if you want to find that what is the safe distance along one side of the axis such that about that axis no tension is developed. Let's say this is a P, and it is here at any centricity E. So if you want to simply check out this E, that for what value of E you are not going to have tension anytime irrespective of the magnitude of load, then how you are going to calculate it? So tension would be developed at the critical surface. So this is my point number 1, this is my point number 2, it is 3, it is 4. So tension would be developed here in this case 1 and 4. So I can take either point, either 1 or 4. So stress at 1 and 4 would be how much? So this would be P upon area. This would be P upon area minus P upon I. Okay, PE upon I into Y. Y is here L by 2. So if I want to keep this stress always equal to 0 or greater than 0, so let me write P upon LB minus PE upon L is how much? It is BL cube by 12. Okay, into L by 2. This I always need to keep greater than equal to 0. So if we are going to calculate so 1 over LB minus 6E by L square B is greater than equal to 0. So L and L cancel, B and B cancel. So E is less than equal to B by 6. Or if on one side if E is B by 6, then on other side it is also B by 6. So indirectly, if we are keeping load in middle third portion, then we will be never getting tension in our column irrespective of the magnitude of the load. Whatever is the magnitude of load, if that load is lying within 1/3 portion, then no tension will be developed. Okay, is it clear? Okay, similarly dear, अगर ये मेरे पास 2D प्रॉब्लम होता तो क्या होता? दिस इज 1/3, दिस इज L by 3. ओके, दिस इज b by 3, this is b by 6, b by 6, b by 6, l by 6, l by 6. So you know, for 2D bending, for combined bending, if you are joining these these 4 points, if you are joining these 4 points, then in this area, wherever you are going to provide load, in this area wherever you are going to provide load, it is never going to give you tension. It is never going to give you tension at any corner. This area is known as kern, K-E-R-N. This area is known as kern. Okay, and here you can see that this column, rectangular column, is going to have this kern. सर यू आर टॉकिंग कंप्रेशन मेजरली ओके सर, इस टाइप के प्रॉब्लम में अनसिमेट्रिकल सेक्शन दे दिया तो प्रॉब्लम लंबा हो जाता है. वेरी यूजफुल एक्सप्रेशन इन डैम. ओके, yes, it is known as curve. This shaded area is known as curve. Is it clear to everybody? ठीक है, ओके. सो आई होप यू ऑल नो कर्व. डेफिनेशन तो नहीं लिखवानी. इट इज दैट एरिया थ्रू विच इफ यू आर गोइंग टू पास द लोड देन टेंशन विल नेवर अराइज. ओके, क्लियर. So you know what is the, if this is rectangular, for rectangular beam, kern is rhombus. Okay, within kern, if load is applied, comma, no tension developed on cross section. ठीक है. अच्छा, कोई आपसे पूछ ले कि यार अच्छा आई सेक्शन के लिए भी आपका कर्न इज rhombus. स्क्वायर सेक्शन के लिए एनीबॉडी, व्हाट इज द शेप ऑफ द कर्व ऑफ स्क्वायर सेक्शन? It is square only. And solid circular section के लिए जो शेप होती है कर्न की, that is circular only. And hollow circular section के लिए जो शेप होती है कर्न की, that is circular only. Okay, yes, it is the safest part of any section. Yes, all circle. For solid circular and hollow circle. And in case of circular, the diameter, I think it is coming out to be 1/8. Yes. And the middle portion is d by 4, 25% of the diameter. Okay, 25% of the diameter is safe. In middle, 25% is safe in case of circle. You can also check. Suppose if we do have circle, if we do have circle, and let's say suppose we are going to check it. सीधी लाइन नहीं है. So if this is the position of load, let's say this one, then here P upon area, pi by 4 d square, minus P into E upon I into Y is greater than or equal to 0. So P और P cancel, pi and pi cancel, d square से d cancel, और ये हो जाएगा 16. Yes, E is less than equal d by 8. So it is d by 8. So it is locus is symmetrical. So it is going to be like this. So this is the kern here. and this portion is middle 25%. Okay, so क्वेश्चन पूछ सकता है कि व्हाट इज द रेशियो ऑफ एरिया ऑफ कर्न टू द टोटल एरिया ऑफ द क्रॉस सेक्शन, ऐसे करके दे कुड हैव आस्क्ड यू सेवरल क्वेश्चंस। क्लियर है कि नहीं है? कोई डाउट तो नहीं किसी को यहाँ तक? कोई डाउट किसी को यहाँ तक? टेल मी एनीबॉडी, एनी डाउट? चलो आगे बढ़े। नाउ नेक्स्ट इज स्प्रिंग। स्प्रिंग में भी चलो वैसे सिविल में तो नहीं है रिक्वायर्ड, बट यस स्प्रिंग इज दिस इज क्लोज्ड कॉइल हेलिकल स्प्रिंग, इट इज आल्सो नोन एज CCHS, क्लोज्ड कॉइल हेलिकल spring. If this is a load on a spring and these are the number of turns, okay, so the strain energy stored in a closed coil helical spring is given by 32 p square r cube n upon GD4. N is the number of turn, G and D diameter, G shear modulus, and R is radius of circular turn. Okay, P is the axial load. And we all know that how we do the calculation in series and parallel. So if this is you can say a series connection, then here the K equivalent would be product by sum. Here the K equivalent would be product by sum. Okay, and if it is a parallel arrangement, then it is simply addition of the individual stiffnesses. It is K1 plus K2, and we can calculate combined. So here it is K, so it would be K by 3, it would be K by 3, it would be K by 3, and this K by 2 and K by 2 is there, and these both are parallel, so they would be becoming K only, and these three are parallel, they would be becoming K only, so K, so overall answer is K by 3, because again this and this would be in series, so overall answer would be K by 3. अच्छा कलो ठीक है, ये बहुत है बस स्प्रिंग के लिए ना, छोड़ो ना। इस पे आते हैं, शियर सेंटर पे आते हैं। ठीक है, शियर सेंटर पे आते हैं। व्हाट इज शियर सेंटर? दिस इज इंपॉर्टेंट, छोटा टॉपिक है बट इंपॉर्टेंट है। व्हाट इज शियर सेंटर? यस, व्हाट इज शियर सेंटर? Shear center is that point in your beam, in your structure, through which if you are going to pass, through which, ये देखो क्या बात है, ये कुछ ज़्यादा ही मजे लेने आए हैं। Shear center is that point through which if load is going to pass, then there will not be any twisting, only bending movement will occur, only bending movement will occur. Okay, only bending movement will occur. ठीक है, और सॉरी ओनली बेंडिंग विल अकर। मतलब जैसे अगर मैं आपसे बोलूं कि यार मेरे पास ये क्रॉस सेक्शन है, ओके, तो ये क्रॉस सेक्शन है मेरे पास, तो अगर मेरे को यहां से लोड पास करवाना है, देन इट मस्ट पास थ्रू दिस पॉइंट। सो मेरा लाइन ऑफ एक्शन होना चाहिए मे बी लाइक दिस और मे बी लाइक दिस, कि ये आप कहीं से पास हो जाए, और मे बी लाइक दिस। So if we simply want to avoid twisting, okay, and if we can only able to analyze bending, then we have to make sure that our load is passing through shear center. ठीक है, चलो कोई नहीं, आपकी एकाग्रता देखने आए हैं कि आप डाइवर्ट होते हो कि नहीं होते। अरे यार बैन करूं, मैसेज लिखूं, ये करूं, वो करूं, कोई बात नहीं, पढ़ लो, छोड़ो, है ना। दिक्कत क्या है? क्लियर है कि नहीं है? चलो ये है, सो दिस इज द केस शियर सेंटर। सो इट इज दैट पॉइंट। देखो इसको एनालाइज करना इसलिए भी जरूरी होता है कि जो भी आप बेंडिंग थ्योरी पढ़ते हो, जो भी आप थ्योरीज वगैरह पढ़ते हो, टॉर्जन के लिए अलग थ्योरी होती है, बेंडिंग के लिए अलग होती है, इसके लिए प्योर बेंडिंग इक्वेशन लगाते हो। सो इन ऑर्डर टू अवॉइड द कॉम्प्लिकेशन, in your structure, you need to identify the shear center so that you can plan the CG of your load in such a manner that it could pass through your shear center, or it could have the least eccentricity in practicality about your shear center, so that in case if we cannot stop torsion or torque, at least we could minimize it. Okay, so that is the reason. Okay, चलो, तो ये है shear center का फंडा. अब shear center को निकालने के कुछ नियम होते हैं, जैसे कई क्रॉस सेक्शंस होते हैं, उसमें आप क्विकली उनको देख के उनका shear center बता सकते हो. ठीक है, जैसे there are some thumb rules to identify shear center. What are they? जैसे shear center will always going to lie on the axis of symmetry. हमेशा अगर axis of symmetry है तो shear center वहीं होगा. भाई कैसे? जैसे ये मान लो it is axis of symmetry, you will be finding your shear. Circle का हो गया, circle is going to have axis of symmetry, you will be finding your shear center. Clear है? But in case if there is more than one axis of symmetry, then it will lying as the intersection. It will lying in the intersection. देखो जैसे यहाँ पे ये भी axis of symmetry है, ये भी axis of symmetry है, तो ये आपके intersection पे आ रहा है. अगर ये तो ऐसे स्ट्रक्चर है कि इनके अगर एक्सिस ऑफ सिमेट्री नहीं भी होती तब भी आप शेयर सेंटर निकाल देते ऑन द बेसिस ऑफ वन एक्सिस ऑफ सिमेट्री. ओके, एंड इफ सेक्शन इज मेड अप ऑफ टू नैरो रेक्टेंगुलर पोर्शन, then your shear center will be located on the intersection of axis of the symmetrical of both of the rectangle. अब ये भी अच्छा पॉइंट है. ये क्या बोल रहा है, जैसे मान लो मेरे पास एक यार ये बन गया, एक मेरे पास ये बन गया. अब मैं आपसे पूछ रहा हूँ इसका shear center कहाँ है, तो ये आपसे सिंपली बोल रहा है भैया परेशान होने की जरूरत नहीं है, दो रेक्टेंगल के से मिलके बना है. लो, एक एक्सिस ऑफ सिमेट्री ये हो गई, एक एक्सिस ऑफ सिमेट्री ये हो गई, जहां पे दोनों मिल रहे हैं वो आपका shear सेंटर हो गया. आर यू गेटिंग द पॉइंट और नॉट? ठीक है, तो ये आपका क्या हो गया, shear सेंटर हो गया. ठीक है, तो इस तरीके से आप निकाल सकते हो. सो देयर आर सम थंब रूल्स. अच्छा, यहाँ पे shear सेंटर कहाँ होगा? इट इज हैविंग टू एक्सिस ऑफ सिमेट्री, इट वुड बी हियर. It is having two axes of symmetry, it would be here. It is having no axis of symmetry but intersection is here. It is having two rectangular, it is here. So these are the possible ways to locate. It is not center of mass. No, please do not confuse with the center of mass. है ना, यहाँ पे center of mass थोड़ी ना यहाँ पे आता है, इधर center of mass यहाँ थोड़ी ना आता है. ये वो सेंटर है जिसके अबाउट आपकी इसेंट्रिसिटी डेवलप नहीं होती है, और इसेंट्रिसिटी डेवलप नहीं होगी तो टॉर्जन नहीं होगा. इट इज नॉट सेंटर ऑफ मास डियर दक्ष. आर यू गेटिंग द पॉइंट और नॉट? क्लियर है? ओके, बट देयर आर सम डायग्राम्स लाइक सी सेक्शन. अब सी में क्या करोगे? ठीक है, इस सी सेक्शन का आपका shear सेंटर एकदम मैन्युअली कैलकुलेट करना पड़ता है, एनालिटिकली निकालना पड़ता है. सो यू गाइस कैन रिमेंबर द डायरेक्ट रिजल्ट. सो इट इज E is the shear center from this outermost you can say web line. It is B square H square T upon 4IX. अगर मेरे पास ऐसा सेक्शन है then it is 4R upon pi, और यू कैन से इट इज 1.27 R. अगर मेरे पास छोटा सा ओपन सर्कुलर ओपन सिल्ट सेक्शन है देन इट इज अगेन E. E इज सिंपली ट्वाइस ऑफ R, ट्वाइस ऑफ 1.27 R. ओके, सो रिमेंबर दिस 6-7 केसेस. ये तीन फॉर्मूले याद रख लेना डियर. ये R E तो वही है 2R, ये फॉर्मूले याद रख लेना. और इसका रेक्टेंगुलर स्ट्रिप का एक्सिस ऑफ सिमेट्री से इंटरसेक्शन से निकाल लेना. That's all. अगर सेक्शन के पास एक ही एक्सिस ऑफ सिमेट्री है then shear center will pass through there. Then shear center will pass through there. होलो सर्कल और ओपन सिल्ट में डिफरेंस क्यों है? अच्छा देखो डिफरेंस क्यों है इसके अंदर. इट इज अबाउट अगर ये कंप्लीटली क्लोज्ड होता, ठीक है, अगर ये कंप्लीटली क्लोज होता डियर देन इट वुड बी सेंटर, बिकॉज मल्टीपल एक्सिस ऑफ सिमेट्री आर गोइंग टू पास थ्रू सेंटर ओनली डियर. but due to this open dip, okay, due to this open dip, it is acting like C section. इसके अंदर जो प्रॉपर्टी आ गई वो किसकी आ गई? C section की आ गई. And on C section, center is deviated on one side. So here as well you can see center is deviated one side. But had it been a case of hollow circular, then it would be having multiple axes of symmetry, and the shear center must have passed through the center of the circle. Okay. Clear hai? Is it clear here? Okay. It is not connected now. It is not uniform now. It is going to act like a C section. Are you getting the concept, ऋषिकेश? चलिए अब स्टार्ट करते हैं अपना आखिरी टॉपिक, ड्रैगन टॉपिक. ये है हमारा स्लोप एंड डिफ्लेक्शन. ये हमारा स्लोप एंड डिफ्लेक्शन. एक ब्रेक ले लेंगे इससे पहले. स्लोप एंड डिफ्लेक्शन चालू करने से पहले एक ब्रेक हो जाए. 1.5 घंटा मिनिमम, 1.5 से 2 घंटा चलेगा. 1.5 घंटा तो चलेगा ही चलेगा टॉपिक ये. ठीक है. Yes, it is most important topic. So I want you guys to be refreshed. मैं भी रिफ्रेश होके आ जाता हूँ. ठीक है. चलिए डियर, एक ले लेते हैं, ब्रेक ले लेते हैं. So we will be meeting at 4. कितना हो रहा है? 4-2 हो रहे हैं, 4-7 हो रहे हैं, 4-7 हो रहे हैं, 4-12, 4-13, 4-15 पे लेते हैं, है ना. We will be resuming at 4:15. 4:15 पे आते हैं. ठीक है. चलो 4:15 पे we will be meeting. So चलो करेंगे आराम से. ये मेरा फेवरेट टॉपिक भी है, और फेवरेट चीजें आपको पता है लोग आखिरी में बचा के रखते हैं. चलिए ठीक है. I will be giving you all the entire important aspects. Okay. So start करने से पहले I will be showing you some standard results. So अगर कोई कैंटिलीवर बीम के एंड पे लोड P लग रहा है, then it is going to show you some slope and delta. This deflection is PLQ upon 3EI and slope is PL square upon 2EI. अगर it is subjected to with some movement, then deflection is ML square upon 2EI and ML upon EI is the theta. Okay. If your cantilever beam is loaded with a UDL on the entire span, then deflection is WL4 upon 8EI and WLQ upon 6EI is going to be this end slope. Okay. This slope you are measuring with respect to the horizontal line. This slope you are measuring with respect to the horizontal line. Okay. If your simply supported beam, ये इतना ज़्यादा रिफ्लेक्ट नहीं होगा, ये थोड़ा मैंने एक्सेजरेट करके आपको दिखाया है. If simply supported beam is subjected with a point load at center, then deflection is PLQ upon 48 EI and end slopes are PL square upon 16 EI. And if UDL is subjected on an entire span of a simply supported beam, then delta is 5/384 WL4 upon EI and theta is WLQ upon 24 EI. Okay. So all these are the standard results. And while few more special cases are there, if UDL is subjected to a land couple M0, so maximum deflection will be occurring at a distance of L/√3 from the far end. And here the theta A and theta B, these are very very important even for your structures. It is ML0 upon 6EI far end slope, and near end slope on which you are applying moment is ML upon 3EI. ये सबको याद होने चाहिए. अगर कैंटिलीवर पे आपने UVL लगाया है, then this is the maximum deflection and this is the slope, maximum slope. Cantilever beam में maximum deflection and maximum slope both are occurring at free end, whereas in simply supported beam maximum slopes are occurring at the ends, and in case of symmetrical loading maximum deflections is occurring at the center of the beam. And if it is not symmetrically loaded, then maximum deflection may be lying to between end to one half of a beam. Okay, so this is the case. Again, if simply supported beam is loaded with some load P, which is deviated A from one hinge end and B from roller hand, then delta is this much. Sir, can you derive any of these equations? Yes, I am going to derive multiple, but before that I am simply going to display you the results. So मैंने आपको 4 से 5 तरीके सिखाने हैं स्लोप एंड डिफ्लेक्शन के, तो हर एक तरीके से आई विल ट्राई कि एक एक केस को मैं जस्टिफाई करता रहूं, ठीक है। सो आई विल बी डिराइविंग इट, डोंट वरी डियर दक्ष। अच्छा, अभी तक सब लोग आए नहीं हो, एक और सेशन को शेयर कर दो ना, एक और सेशन को शेयर कर दो अपने अपने दोस्तों में एंड ऑल, बिकॉज फर्स्ट टॉपिक इज देयर। सो वी विल बी स्टार्टिंग इट नाउ, डियर। ओके, बट आई विल बी गिविंग यू दिस PDF, सो प्लीज मेक श्योर कि ये सारे के सारे स्टैंडर्ड रिजल्ट्स आपके याद हो। दिस इज ऑल्सो इंटरेस्टिंग। अगर फिक्स्ड बीम इज लोडेड विद P at center, then the deflection is PL cube upon 192 EI, which is 1/4 of the simply supported deflection, and if fixed beam is loaded with the P, the W or entire span, then the deflection you are going to get WL4 upon 384 EI, which is 1/5 of simply supported deflection for same loading. Okay, derive भी करेंगे dear, derive भी करेंगे। चलो, so first let us start with the double integration method. Okay, first we are going to start with double integration method. So this is the main equation given by Mohr, and we can ignore this term, okay, because it's derivative ka square and it is going to be very very small quantity. So we can write our double integration equation like this: t square y upon dx square is equal to m upon ei. अभी थोड़ी देर पहले ये इक्वेशन मैंने आपको कॉलम में भी यूज करके दिखाई थी, मैंने कहा था अभी थोड़ी देर बाद बताऊंगा। सो दिस इज योर डबल डेरिवेटिव इक्वेशन। Why we are calling this method double integration method? Because we have to integrate this equation twice. 2 times we have to integrate this equation. First time में आपको मिलता है slope, second time में मिलता है आपको deflection. जब फर्स्ट टाइम में आपको स्लोप मिलता है तो एक कांस्टेंट मिलता है और डिफ्लेक्शन मिलते हैं, 2 कांस्टेंट मिलती हैं। सो बेस्ड ऑन द बाउंड्री कंडीशंस you will be able to calculate these constant, and these constants are helpful in writing the general equation of your slope and deflection. So this double integration method is also useful whenever you want to write the whole equation of slope and deflection, whereas the other methods which we are going to see further, like moment area, conjugate beam, strain energy method, they are going to work only for some particular point. But yes, they are more powerful than your double integration method, because double integration method works on the continuity of slope. Where your slope is not continuous, it is not going to give you result. Similarly, moment area method also works on the slope, continuity of the slope. Where slope is breaking, the answer is not matching. So for that we will be using conjugate beam strain energy method. Okay, so let's start a case with the double integration method. So just to explain the process, let me use a small problem. Like this is a cantilever beam, and this cantilever beam is subjected to UDL. Let's suppose the flexural stiffness of this UDL is constant, EI is constant, and L is the length of the beam. इस पॉइंट को बोल दो A, इस पॉइंट को बोल दो B, ठीक है। इस पॉइंट को बोल दो A, X को बोल दो B, और ये इसका लेंथ हो गया, एंड इसका इंटेंसिटी W हो गया। सो दिस इज माई डबल इंटीग्रेशन इक्वेशन, or this is my double integration equation, means I have to apply double integration on these equations. For this EI is constant, we need to calculate the bending moment. So how I can go for bending moment? If I am going to write equation, let's suppose section 1-1. So what is my M11? M11 is W into X. This is load into X by 2. Or make it negative because it is giving you hogging sense. So this is M11. So now simply put this value in the double integration equation. So my equation was EI d2y by dx2 is equal to M11. It is WX square by 2. It is WX square by 2. As I told you, procedure says that we have to integrate this equation twice. First time if I am going to integrate it, I will be getting EI dy by dx, and if I am performing integration on the right hand side, so x square का integration would be x cube by 3. So 1 by 2 into 1 by 3 is 1 by 6. and one constant will come because the integral is indefinite. Again, on integrating this equation, again we will be getting EIY is equal to WX की power 4 upon 24 plus CX plus D. Now the task is to find the value of this C and D. अब हमें C और D की वैल्यू निकालनी है. तो कैसे निकालेंगे डियर्स की वैल्यू? Like we have to look for boundary conditions. So what is boundary condition here? You can check at x is equal to L, slope is 0 because at fixed end slope is 0, and at x is equal to L, deflection is also 0. Okay, it is x is equal to L, y is equal to 0. Okay, so now my dear friend, what to do? Okay, great, ये तो अच्छी बात है फिर, ठीक है. So अब क्या करोगे आप क्या करोगे डियर? At x is equal to L, dy by dx is equal to 0. So let me rewrite this equation and apply boundary condition. So at x is equal to L, dy by dx is equal to 0. So substitute this. 0 is equal to minus WL cube upon 6 plus C. So from here C is equal to how much? C is equal to how much? WL cube upon 6. Okay. Again, at x is equal to L, y is again 0. At x is equal to L, y is again 0. So d निकालोगे तो d कितना आएगा? d would be minus 1 plus 3. So it is WL4 upon 24. 3 by 24 is 1 by 8 plus d. So d is coming out to be minus WL4 upon 8. So now let me write the equation of slope and deflection. So equation of slope says कि EI dy by dx is equal to minus wx cube by 6 plus c. What is c? c is WL cube by 6. So theta is WL cube by 6 EI minus WX cube upon 6 EI. So now you can check. At x is equal to 0, what is the theta? So theta at B at x is equal to 0, so it is WL cube upon 6 CI. Similarly, if I want to write a second equation of deflection, so which says EIY is equal to how much? Minus WX4 upon 24 plus C plus D. What is D? D is minus WL4. D is minus WL4 upon 8. So deflection general equation is minus WL4 upon 8EI plus WL cube upon 6 into x minus WX4 upon 24EI. So this is a general equation of deflection. So you can check the and deflection at x is equal to 0. The deflection at B is equal to minus WL4 upon 8EI. Okay. One time integration slope, two time integration deflection, exactly. Equation of slope and equation of deflection. But after that you have to play the game of boundary condition. And you can check out these two results, 1 by 6 theta and minus 1 by 8 deflection, or 1 by 8. Focus on the magnitude. और आप कह रहे थे कि इसको मैं करके दिखाऊंगा कि नहीं, आप देख सकते हो. यू कैन मैच द रिजल्ट हेयर. इज इट मैचिंग डियर दक्ष? इज इट मैचिंग डियर हेयर? 1/6 and 1/8. Okay, so this is how we are going to use the double integration method. Okay, so there is one more method like double integration method, which is the extension of double integration method, and that method is known as Macaulay's method. Actually, what is happening when there are multiple loads, occurring here, here, here and here. So in order to incorporate all these loads, you need to make several function of bending moment. Like bending moment, one will run from here to here, second will here to here, third from here to here. So such equation when it takes form is known as Macaulay's method. Okay, I'm not going into that Macaulay's. Okay, I will be teaching you another method for finding slope and deflection, or any other problem you want me to solve by double integration method. So what you can do, dear, what you can do, you can find the results for this case and this case by using double integration method. ये मैं आपको assignment दे रहा हूँ, double integration method से आप ये दोनों find कीजिएगा. Okay, so let me also explain you a case of simply supported beam. Just I want to show you how to use the boundary condition in simply supported beam, dear. Only boundary condition I am going to write. Let's suppose this is a simply supported beam. Okay, and this simply supported beam, I said it is subjected to UDL. Here as well you guys can take EI as constant, and length you can take as L. If this is A, this is B. So what is the bending moment equation? Bending moment equation from either side, it is WL by 2 into X minus W into X by 2. And the good thing is this equation is going to work for entire system. Now if I am going to apply the double integration equation, EI d2y upon dx2, it is M. So d2y upon dx2 is WLX by 2 minus WX square by 2 into EI. Now integrate it twice. One time you will integrate it, you will be getting what? अगर आप इसको एक बार इंटीग्रेट, अरे यार, yes, if you are going to integrate it once, then what you will get, this is the equation. So on one time integration you would be getting EI dy by dx section X. This is the section here. This reaction is WL by 2. So it is WL by 2 into X sagging minus W into X into X by 2. This is hogging, so I placed here a negative sign. So this is how much? WL X square by 4 minus WX cube by 6. Again on integration, what will you obtain? Can you tell me how to find C and D? Anybody? Can you tell me how to find C and D? What can be the boundary condition here? Anybody? बताएंगे क्या होगा? I am interested in boundary conditions. No dear, no Daksh, not at all. This is not the boundary condition. Tell me, do you really think that at x is equal to 0, dy by dx is equal to 0? In fact, you are telling it in the reverse order. At x is equal to 0, the slope is maximum. It is not 0. Yes, Ashraf is right. At x is equal to L by 2, slope is 0. Yes, this can be the boundary condition in case of symmetrical loading. But let me tell you, I am taking the non-symmetrical loading case. Now, what can be the, जिसको कहते हैं ब्रह्मास्त्र बाउंड्री कंडीशन क्या हो सकती है सिंपली सपोर्टेड बीम के लिए? What can be the universal boundary condition for simply supported beam? So you can check out here. At x is equal to 0, deflection is 0, as well as at x is equal to L, deflection is 0. So who told you to use both the equations for boundary condition? Try to use the fact. Fact is this: at near end as well the deflection is 0, at far end is also deflection is 0. So if I am going to use this one, so place 0, 0, 0, y is also 0. So from here d is coming out 0. Okay. So d is 0, remove it. I am removing the d. Why I am removing the d? Because at x is equal to 0, y is equal to 0. From there d is coming out to be 0. Next, at x is equal to L, y is again 0. At x is equal to L, y is again 0. So it is WL4 by 12 minus WL4 by 24 plus C into L. So this is the value of C. C is how much? It is minus WL cube upon 24. This is the value of C. Are you getting the point or not? If C is this much, then the general equation is EI theta, or general equation for theta is how much? WLX square by 4 minus WX cube by 6 EI minus WL cube upon 24 EI. You can check at x is equal to 0, a slope is minus WL cube upon 24 EI. At x is equal to 0, slope is WL cube upon 24 EI. So this we can also check. So these two are the, so what is the universal boundary condition for cantilever beam? At fixed end, slope is 0, deflection is 0. What is the universal boundary condition for simply supported beam? At both supports, deflection is equal to 0. Are you getting the point or not? So like this you can solve the problems on slope and deflection by using double integration method. And you know one good thing about double integration method, by using it you even can solve indeterminate structure. For example, we all know that this probed cantilever beam is indeterminate structure. We all know that fixed beam is indeterminate structure. With the help of double integration method, sir, you said double integration method is good for SSB, moment area method for cantilever, and strain method for any type of beam and frame. Yes, I told it once, and that is also right. Double integration method is good. Actually, what I told, I am reminding you because I generally say same things all the time. Double integration is only useful whenever you need continuous result. You need the equation of slope and deflection. Moment area method you can apply whenever there is a case of cantilever beam, or if it is a case of simply supported beam, but simply supported beam must be symmetrically loaded. And if simply supported beam is not symmetrically loaded, in that case you can go for conjugate beam. And whenever your simply supported beam is subjected to internal discontinuity like internal hinge, still you can go for conjugate beam. But whenever you want to tackle any kind of problem which is not able to solve easily by any of these methods, go for strain energy method, because the strain energy method is universal method. It is applicable for trusses, it is applicable for frames, arches, for each and every kind of frame. That strain energy method is useful. Okay. Yes. Okay. So have you taken my course on YouTube, Ashraf, which I taught in 2020, I guess, on theory of structure? In that course, I explained these methods in very much detail. है ना? तब तो हमने इसको काफी डिटेल में किया था. 1.5 साल हो गए, 1.5 साल हो गए, 1.5 साल से ऊपर ही हो गया. चलिए, आई थिंक जुलाई वगैरह में, हाँ 1.5 साल हो गया. उसके बाद तो मैंने मैराथन क्रैश कोर्स जैसी चीजें ली हैं, है ना, तभी पढ़ाया था मैंने स्ट्रक्चर आपको. चलिए डियर, दिस इज अ केस. So yes, I told you that here suppose if you have some load, so there are one unknown, additional unknown, because 3 we can solve by equilibrium equation, and there are 2 constants C and D. So here the total unknown parameters are 3. Okay, the first lecture I saw in Unacademy, I am following that in this year. Okay. First lecture, but I took off RCC. I remember the very first lecture which I took on 5th of May 2020 was of RCC, and that was the recorded lecture. Okay. After that RCC, I started structure, full length course on structure. ठीक है, चलो. So R, C and D are there. R, C and D are there. Okay. So for these 3 values, you will be having 3 compatibilities or 3 boundary condition. So can anyone suggest me what all are the boundary condition in this case? Please suggest me the boundary condition in probed cantilever beam. Please keep one thing in mind. You will be needing 3 boundary condition now. So here the boundary conditions, 3 unknowns are there. At x is equal to 0, y is equal to 0. At x is equal to L, y is equal to 0. And at x is equal to L, dy by dx is also equals to 0. So with the help of these 3 boundary conditions, you will be able to obtain this R, C and D. So your structure is solved now. Similarly, if suppose some load is acting here, so here as well you will be needing some boundary condition. So total for vertical loading, its static indeterminacy is coming out to be 2. 1 reaction, 1 moment, 1 reaction, 1 moment. So you can tackle only 2. So 2 unknowns are there, R1 and R2 or M1 or R2 or whatever, and 2 constants are there. So what all are, how many boundary conditions we do need here? 4. At x is equal to 0, slope is 0. At x is equal to 0, deflection is 0. At x is equal to L, slope is 0. At x is equal to L, deflection is 0. So by using these 4 boundary conditions, you will be able to calculate all these 4 unknown parameters, and your structure becomes quite solvable. Yes. Is it clear? So this is the way to use boundary condition. So this is the advantage of using double integration method, because it also helps sometimes in your structures. Okay, for plane structures without internal discontinuity, even it is indeterminate, you will be able to solve it. Okay, but it is slightly lengthy. It is slightly lengthy if you do not know the standard result. If you know the standard results, then I will recommend other methods. like moment area method, conjugate beam method, and strain energy method. Okay, now the second method to calculate slope and deflection, which is also very famous, is known as area moment or moment area method. It is known as moment area method. So in moment area method, also it is suitable for cantilever, and it is also suitable for simply supported beam if it is symmetrically loaded. If it is symmetrically loaded. Okay, symmetrically loaded may be like this, it may be like this, or it may be like this. So all these are the various symmetry, or it may be like this. Okay, so in such cases you can use the moment area theorem. Okay, ओवरहैंग बीम में भी आप इसको यूज कर सकते हो. हाँ, ओवरहैंग बीम में भी आप इसको यूज कर सकते हो, बट अगेन आई विल से कि सिमेट्री होनी चाहिए. ठीक है, तो यूज तो आप कहीं भी कर सकते हो, बस इंटरनल हिंज नहीं चाहिए. बट होता क्या है ना कि कैलकुलेशन कॉम्प्लिकेटेड हो जाती है. ये जो मैं आपको कैंटिलीवर और सिंपली सपोर्टेड बीम विद सिमेट्रिकल लोडिंग बोलता हूँ ना, ये इसलिए बोलता हूँ बिकॉज यहाँ पे आपकी थोड़ी कैलकुलेशन पॉइंट ऑफ व्यू आसान हो जाती है. ठीक है, so we do have two theorems in moment area. Okay, the theorem 1 is talking about change of slope. Theorem 1 talks about change of slope. Theorem 2 talks about vertical deviation. It is talking about vertical deviation. So either you are using theorem 1 or theorem 2, you need to know the address, or you need to know the slope and deflection of at least one point. And in cantilever beam, fixed reaction is a point where slope and deflections are known, that is equal to 0. So that is the reason why I used to say you can use this method in cantilever beam. And why I am even recommending it for simply supported beam loaded symmetrically, because in symmetrically loaded simply supported beam also you know these points. You know slope is always 0 in simply supported beam at center if it is symmetrically loaded. You know, slope is maximum at the ends. You know, deflection is always maximum at the end. So you know the addresses here. Okay, you know the deflection at end is equal to 0 in simply supported beam. ओके, यस, कर्वेचर डायग्राम इजी हो जाता है, सिमेट्रिकल हो जाता है. सो आई यूज टू कीप टेलिंग दिस पॉइंट एज वेल, दैट व्हेनेवर योर सिंपली सपोर्टेड बीम इज सिमेट्रिकली लोडेड, रिएक्शंस से इलास्टिक कर्व सिमेट्रिकल, बेंडिंग मोमेंट डायग्राम सिमेट्रिकल, शियर फोर्स डायग्राम एंटी सिमेट्रिकल, एंड स्लोप्स मैक्सिमम, central deflection maximum, central deflection 0. So you need you can blindly trust on these points which I am telling you if you have your simply supported beam symmetrically loaded. Okay, so half of the problem is taken care by symmetry itself, और बचा हुआ half के लिए आप लोग वही, आपको भी तो नंबर लेने हैं. So that is the case. So what is the first theorem? It says the change in slope from any point x to b, let's suppose if this is any point x and this is b, and this is equal to the area of m upon ei diagram bounding between this point x and b. Okay, let's suppose it is a elastic curve. Let me draw the elastic curve. So this is your point x. Please mention a point here that x and b are on elastic curve. X and b are on elastic curve. This is x and this is your b. So this change in slope is equal to area of m upon ei diagram bounded between b and x. So suppose this is area of m upon ei diagram. This is area of m upon ei diagram. Okay, this is m upon ei diagram. Can anybody tell me why this slope and deflection is also a function of E and I? Why this slope and deflection also a function of E and I? It is quite obvious that due to the bending moment, more deformations, more elastic, more curvature of elastic curve, so more value of slope and deflection. But why it is depending upon E and I? Because this slope and deflection is not only of the function of action but also of the resistance of your material. So anyway, you all know that if same load is applied onto different material, let's say one is copper and another is aluminum, or third one is steel. So all these three uniform cross section, although they are having same end condition, they are going to give you different value of slope and deflection as per their material capacity. So this slope and deflection is the function of action as well as of reaction. So that's why we need to incorporate one parameter of material property, so that is E here. Also we are working in terms of bending. So for bending, EI is flexural rigidity. And why I is here? Because this cross, although if you are having same material of same cross section, but if you are changing the orientation of your cross section, its moment of inertia may change, like in case of rectangular beam, I section, channel section and all. So these neutral axis about which neutral moment of inertia is more, it is going to have less deformation against slope and deflection, against the external bending moment. So that's why your slope and deflection is also a function of your geometrical property, which is the moment of inertia. Yes, is it clear to all? लाइक इसको समझाने के लिए कॉमन एग्जांपल देते हैं कि यार यही मेरा मान लो पैड है, मान लो यही मेरा राइटिंग पैड है, ठीक है. So it is going to deflect like this easily, but it will not going to deflect like this, because here the moment of inertia you can see more, small b is there and a huge d is there, so bd cube by 12 would be very high. But when I am comparing here, so this is a section which is getting bent. So here b is high but d is small and d cube is there. So here bd cube value is quite less, it is quite nominal. So that's why bending is easy about this axis. Is it clear? Yes, for a material E and I are constant. For a material E and I are constant. For a material E is constant, and for beam is prismatic only, it is going to remain same. But two different in which orientation can change. So I am comparing the slope and deflection in those areas. Okay, so this is the theorem number 1. What does theorem 2 says? Theorem 2 says that if you want to find deflection of any point B with respect to tangent drawn from any point X, it is equal to the moment of area of M upon EI diagram between X and B about B. If you are calculating deviation of B with respect to X, then you have to calculate it about B. If you are calculating deviation of X with respect to B, then you need to calculate it about X. Okay, so this moment is to be taken about that point where we are going to calculate deviation. Actually, again I would like to say, if this is my deformation pattern, it is my deformation pattern, and let's say this is my B point, and let's say this is my X point. And if I want to simply know what is B deviated from the tangent drawn from X, let's say the tangent drawn from X is this much, the tangent drawn from B is this much. So this is deviation of B with respect to tangent drawn from X, and this deviation of B with respect to X is equal to the, this is equal to the deviation of B with respect to X is equal to the area of M upon EI diagram into its CG, into CG from B, CG from B. So this deviation is to be taken about that point where we need to calculate. The CG is to be taken about that point where deviation is needed. So this is theorem number 2 of moment area. So I want to show you the small application. So let me take a problem on cantilever beam. This time I am taking point load. Let's suppose this is L and EI is constant. This is A, this is B. Suppose I want to know theta B and deflection at B, the very first case. So how to tackle? So this is M upon EI diagram. You know that what is this value? Beam with different EI also ले लूँ, चलो ठीक है. Okay, beam with different EI भी ले लेता हूँ. Let's suppose this is 2 EI and let's suppose this is EI and this is L by 2. This is also L by 2. अब ठीक है. So this is 2 EI, this is EI. Okay, so now if we are going to draw the bending moment diagram, it is like this. Bending moment diagram is not going to change, it is minus P into L. But M upon EI diagram will change. M upon EI diagram will change. Why it will change? Because this time the EI is EI here, but it is 2 EI here. So whenever you are going to draw the M upon EI diagram, अगर मैं यहीं पर minus M upon EI diagram बना दूँ, minus PL upon EI, या चलो अलग बना देता हूँ, minus M upon EI, so it will going straight here, PL by 2 upon EI, suddenly it will be facing some drop, then again it will come here. So this value is basically what? It is PL by 2, na? It is PL by 2. So what about this value? It is PL upon 2 EI. Then again it will be falling to PL upon 4 EI, because the moment you are going just right to it, just left to it, flexural rigidity is just double. So again it is again PL upon 2 EI. So now if you want to calculate theta B dear, then calculate it reference, and reference is theta I, because at A slope is 0. So this is the elastic deformation. Okay, so you need to calculate theta B. So how you are calculating theta B? Theta B is change of slope between B and A slope is 0. So whatever change is there of B with respect to A is the ultimate absolute value of slope. So this is area of M upon EI diagram between A and B. So this is area of this triangle plus area of this trapezium. So let me divide this trapezium further into rectangle and triangle. So area of this triangle is half into base into height, plus area of this rectangle is PL upon 4 EI into L by 2, plus area of this triangle is half into base into height. So this theta B is PL square upon 8EI plus PL square upon 8EI, okay, plus PL square upon 816 EI. तो कितना हो गया? थीटा बी जो आएगा आपके पास, that would be how much? 8, 2 और 2 4 4 5 5 PL square upon 16 EI. Are you getting the point or not? Okay, this is 5 by 16 of EI. Similarly, if you want to calculate deflection also you can calculate. For deflection, what you can do? You can draw the tangent from A and you can extend it till B. So the distance between these two tangents is nothing but the deviation of B with respect to A, which is also known as the deflection at B or end deflection. So end deflection here is deviation of B with respect to A, and if you want to calculate deviation of B with respect to A, then first of all you have to take the moment of all the area entrapped between these 2 points about B, because we need to calculate deviation about B. Okay, so CG calculation we have to do about B only here. So this area is triangle, so it is half into base into height. It is half into base into height. I am not giving importance to sign here, although it should be negative, and its CG is 1 by 2 by 3 of L by 2 plus this is the rectangle. This is the rectangle. What about this rectangle? It is P L upon 4 EI into L by 2 into its CG is L by 2 plus half of L by 2. It is half. Okay, so like this you can calculate, and you will be able to calculate the deflection at B. So this is the procedure to use movement area method here. This is the procedure to use movement area method. Tell me if any one of you is having any doubt. कोई डाउट किसी को यहाँ तक? Anybody? कोई डाउट किसी को यहाँ तक dear? Tell me. ठीक, कैलकुलेशन नहीं कर रहा हूं मैं. So this is the movement area method. So do you want me to take one more problem for movement area? Deflection समझ में नहीं आया दक्ष? क्या लिखा था देखो यहाँ पे, What did theorem 2 says? अगर मैं आपको b with respect to x निकालना है तो आपने ये टेंजेंट कितना डिवाइडेड है इससे ये पता लगाना है. तो आपने x और b के बीच का एरिया ले लिया और इसका cg ले लिया अबाउट b. ठीक है, यहां पे जो एरिया ट्रैप्ड हुआ ये 3 हिस्सों में मैंने बांट दिया. एरिया नंबर 1, एरिया नंबर 2 और एरिया नंबर 3. सो डेविएशन ऑफ बी विद रिस्पेक्ट टू ए निकाल रहा हूं. सो बी से ए तक का जितना भी एरिया सारे का मोमेंट लेना पड़ेगा. किसके अबाउट लेना पड़ेगा? बी पॉइंट के अबाउट लेना पड़ेगा. तो ये मोमेंट मैंने एक एक करके ले लिया. ये पहले वाला मेरा ट्राइंगल था, हाफ इंटू बेस इंटू हाइट कर लिया. तो हाफ, मैं इसको यहां दोबारा प्लॉट कर देता हूं, जरा देखना ध्यान से. इसको मैं यहां प्लॉट कर रहा हूं डियर, चेक करिएगा. ओके, नाउ सी दिस वन, हाफ इंटू बेस इंटू हाइट, और सीजी कितना होगा इसका? ये व्हाट इज दिस सीजी? 2 by 3 ऑफ L by 2. नेक्स्ट रेक्टेंगल L by 2 इंटू हाइट, सीजी कितना हो जाएगा इसका? ये L by 2 प्लस हाफ ऑफ L by 2 मतलब L by 4. थर्ड ग्रीन वाला देख लो, हाफ इंटू बेस इंटू हाइट, हाफ इंटू बेस इंटू हाइट, सीजी कितना हो जाएगा इसका? L by 2 प्लस 2/3 ऑफ L by 2. क्लियर है? क्लियर है? नो सर मीन सचिन, क्या समझ में नहीं आया? आपको भी कुछ समझ में नहीं आया? टेल मी दक्ष. ऑल क्लियर? ओके. सचिन, इज इट क्लियर एवरीथिंग? क्लियर है? ओके, सो दिस इज द केस. चलिए, सो टेल मी. अच्छा, कोई और क्वेश्चन? ओके, ग्रेट. एनी अदर क्वेश्चन? एनी अदर क्वेश्चन? सिंपली सपोर्टेड का भी ले लूं, एक सिमेट्रिकली लोडेड का रिक्वायर्ड है? टेल मी. So now you can attempt the cantilever beam uniformly loaded with the UDL by this method. Okay. Okay. चलो. So चलो एक याला ले लेते हैं. This is P, this is A, this is B, and we take this is L by 2, this is L by 2, and we need to calculate deflection at C and theta at A. Okay, so first of all we can draw the bending moment diagram. Bending moment diagram here is quite symmetrical. एंड ई आई कॉन्स्टेंट ही ले लेते हैं इस बार, और ई आई कॉन्स्टेंट ले लेंगे तो दिस ऑर्डिनेट इज कमिंग आउट टू बी पी एल अपॉन 4 ई आई. ओके, दिस इज 0, दिस इज 0. सो डायरेक्टली आई हैव ड्रॉन हियर एम अपॉन ई आई डायग्राम. ओके, नाउ इलास्टिक कर्व जो इसका बनेगा डियर, दैट वुड बी लाइक दिस. अच्छा, अच्छा ट्विस्ट लगेगा. अच्छा ठीक है. अच्छा, एक चीज और मैं आपको बताना चाहता हूं. रिसेंटली आई हैव कंप्लीटेड ए सीरीज ऑन स्लोप एंड डिफ्लेक्शन ऑन अनअकैडमी स्पेशल क्लासेस. ठीक है, तो जो लोग रिकॉर्डेड देख सकते हो तो आप उसको वहां भी देख सकते हो. सो ऑन स्लोप एंड डिफ्लेक्शन आई हैव टेकन अप्रोक्सीमेटली 9 to 10 लेक्चर्स. थंबनेल भी ऐसे ही है, स्लोप एंड डिफ्लेक्शन लेक्चर 1, स्लोप एंड डिफ्लेक्शन लेक्चर 2, लाइक दैट. तो आई हैव टेकन 10 सेशंस ओनली ऑन स्लोप एंड डिफ्लेक्शन. ठीक है, तो अगर आपको मोर नंबर ऑफ न्यूमेरिकल्स चाहिए या वेरी, तो आप उस केस में स्पेशल क्लास भी देख सकते हो मेरी. ठीक है, तो ये हो जाएगा सीन मेरे पास लाइक दिस. चलिए, सो दिस इज अ केस. नाउ व्हाट विल हैपन? थीटा ए, it is symmetrically loaded, and whenever it is symmetrically loaded, so without any hesitation you can assume that central slope to be 0. ठीक है, central slope to be 0 without any hesitation you can assume. So this is the theta. So suppose if you want to calculate theta A, then I would like to keep it like this. Theta C I can calculate with respect to A. Theta C I can calculate with respect to A. It is theta C minus theta A, and theta C is the central slope which is 0. And what is C with respect to A from moment area theorem? C with respect to A, फ्रेम का एक आधा ही न्यूमेरिकल होगा. कहो तो फ्रेम अभी करवा दूंगा मैं, कोई दिक्कत नहीं है. ठीक है, फ्रेम अभी करवा दूंगा. So this is theta A. So area of M upon EI diagram bounded between A and C. So you can see the bounded area between A and C is nothing but a triangle only. ये triangle है. तो ये कितना हो जाएगा डियर मेरे पास? It would be half into base into height. That's all. भाई क्या करूं, मैराथन का मतलब यही होता है. मैराथन का मतलब यही होगा. अभी तो और सुनोगे. अभी 7:15 से स्पेशल है, फिर 10 बजे से भी स्पेशल है. So theta A is PL square upon 16 EI. Theta A, this negative will come here. So PL square upon 60 EI. Tell me clear? हाँ, डिफ्लेक्शन निकालना यहाँ पे थोड़ा ट्रिकी है, डिफ्लेक्शन निकालना थोड़ा यहाँ पे ट्रिकी है, खास करके सेंट्रल डिफ्लेक्शन। सेंट्रल डिफ्लेक्शन कैसे निकालोगे यहाँ पे? इफ यू वांट टू फाइंड सेंट्रल डिफ्लेक्शन, टेल मी व्हाट वुड यू लाइक टू कैलकुलेट? Will you be calculating deviation of C with respect to A, or you will be calculating deviation of A with respect to C? Like when we calculated central deflection at B, we calculated deviation of B with respect to A. We calculated deviation of B with respect to A. But tell me in this case, what you want me to calculate? Red वाला deviation of C with respect to A, या फिर blue वाला deviation of A with respect to C? एवरीबडी, ओपन क्वेश्चन है फॉर ऑल। ए के अबाउट लेंगे मूवमेंट डायग्राम, ए के अबाउट लेंगे मूवमेंट डायग्राम। वेरी गुड सचिन, सही बोल रहे हो। क्यों? बिकॉज व्हेन इट इज डेविएशन ऑफ ए विद रिस्पेक्ट टू सी, हाँ, तो क्या होगा? आई हैव टू ड्रॉ टेंजेंट फ्रॉम सी, I have to draw tangent from C, and this tangent will be coming till A. Luckily at C the tangent is horizontal, and till A it is going to travel in a horizontal manner. So now the deviation between these two tangents is nothing but magnitude wise it is equal to the central deflection. So that is the reason why I told you that it is tricky one. So deviation of A with respect to C is going to work for you here. Yes, you can also calculate it through red one, but from that procedure is lengthy. I will also explain you how. You can also calculate it from red one. You can also calculate it from deviation of C with respect to A, but procedure is slightly lengthier, but that is solution is universal. Okay. Like deviation of A with respect to C. It is magnitude wise equal to C delta C. It is area of M upon EI diagram bounded between A and C, half into base into height into CG. CG about A now I have to take. So it is 2 by 3 of L by 2. This and this cancel. 12, 24, 48. So PL cube upon 48 EI. It is PL cube upon TI. Okay, that's why I always say to everyone that it's more the teacher, it's more the nation builder than the student. Okay, चलो ठीक है, it's PL cube upon 48 EI. Great. Okay, okay, thanks to you guys as well जो सपोर्ट कर रहे हो मेरा अभी तक। चलिए, अब deviation of C with respect to A we can also calculate. Deviation of C with respect to A we can also calculate. But what you are going to get ultimately? This time you have to originate your tangent from A and it will last to C. So this is what you are going to get if you are going to take the CG of this system instead of about C instead of A. This is what you will be going to get. It is a deviation of C with respect to A. But the thing is, we were looking for this and you have calculated this. We do have a procedure how to convert this red one to black one. Okay, let me make you understand like this. Suppose if delta deviation of C with respect to A we want to calculate, then what is deviation of C with respect to A? It is same area. It is same area, but CG is changed. CG is how much? It is 1 by 3 of L by 2. It is 1 by 3 of L by 2. So what is this? It is PL cube upon 6, दोबारा तो 24, 24 चौके 96. Okay, but this is not what we required, because this is this deviation of C with respect to A. Ultimately we were looking for C. Can anybody suggest me what to do? How can I get the value of delta C? See, delta C you guys can calculate, you know how. Delta C you can calculate, you know how. You can calculate like this. If you are looking for delta C, calculate the value of theta A. That is already calculated. It is PL square upon 16 EI. Theta A into L by 2. Now you can subtract deviation of C with respect to A. Okay. So this is the case. So deviation of C is theta A PL square upon 16 EI into L by 2 minus deviation of C with respect to A is how much? It is just we have calculated PLQ upon 96 EI. PLQ upon 96 EI. तो ये हो जाएगा 1/32 1/36 96 32 या 96 2 minus 1 3 minus 1 2. So it is PL cube upon 48 EI. So see, we can we have reached to same result. Yes, Sachin is right. Sachin is right. ठीक भाई, ये लव फेस वाले को कोई करो यार, कुछ करो इसका यार, ठीक है। इन्हें बोलो भाई ये सब चीजें सिविल वालों के लिए नहीं होती है। रॉन्ग ग्रुप, ठीक है। PL क्यू अपॉन 48 EI, PL क्यू अपॉन 48 EI, ठीक है। You know why this method is quite general? Because अगर आपको कभी क्वार्टर पे निकालना हो डेल्टा, ओके, तो भी आप ये अप्रोच यूज कर सकते हो। Suppose if you want to calculate the deflection at this D point, delta D, then you can adopt this general procedure. It is theta A into L by 4 if D is the quarter of the beam minus deviation of D with respect to A you can calculate, and you will be even able to find the deflection at D. So this is more general, because here you cannot perform the exercise in reverse manner, because if you are going to draw here the back tangent, so this time the back tangent is not equal to deflection at D. Here the back tangent was equal to deflection at C because this tangent was quite horizontal. So that is the reason. ठीक है, क्लियर है कि नहीं है? चलो, हाँ, सो बहुत हो गया मोमेंट एरिया मेथड, और दो मेथड हो गए, डबल इंटीग्रेशन एंड मोमेंट एरिया मेथड. नाउ वी आर हेडिंग टुवर्ड्स मोर पावरफुल टेक्निक which is known as the conjugate beam method, which is known as the conjugate beam method. ठीक है, conjugate beam method का आइडिया है आपको? What is conjugate beam method? Here the beauty is this, it is again applicable for prismatic and non-prismatic member. It is also helpful for beam which contains internal discontinuity like internal hinges. Okay. So what is there in conjugate beam method? जैसे ये ना आपको conjugate beam method एक आपका टूल है, स्लोप एंड डिफ्लेक्शन निकालने के लिए आपको एक टूल बना के जैसे देते हैं ना, ये टूल की तरह काम करता है. ये आपका एक इमेजिनरी बीम है, ठीक है, जिसको आप टेम्परली बनाते हो अपना मतलब निकालने के लिए. ठीक है, होता क्या है कि डायरेक्ट स्लोप एंड डिफ्लेक्शन निकालने से अच्छा हम लोग एसएफडी बीएमडी में ज़्यादा कंफर्टेबल होते हैं. तो कंजुगेट बीम रियल बीम के हिसाब से एक ऐसा बीम बन जाता है जिस बीम में अगर आप शियर फोर्स निकालते हो तो आपको रियल बीम के स्लोप्स निकलने लग जाते हैं. जिसमें आप बेंडिंग मोमेंट निकालते हो कंजुगेट बीम में तो वही बेंडिंग मोमेंट रियल का डिफ्लेक्शन बन जाता है. तो हम लोगों को आदत होती है एसएफडी बीएमडी इजीली कैलकुलेट करने की रेदर देन स्लोप एंड डिफ्लेक्शन. बट हाँ, उसके लिए आपको एक टूल दिया गया है इनडायरेक्टली मैं ये कहूंगा कि आप मोमेंट एरिया मेथड ही लगा रहे होते हो कंजुगेट बीम के अंदर, बट आपको पता नहीं चल रहा होता कि वो कैसे लग रहा है, क्योंकि आप निकाल रहे हो अपने कंजुगेट बीम में शियर फोर्स बेंडिंग मोमेंट, उसमें आप सब लोग एक्सपर्ट हो, बट अल्टीमेटली वो स्टेप्स रियल बीम में अगर आप उसको प्रोजेक्ट करोगे तो वो स्लोप मोमेंट एरिया मेथड वाले ही आएंगे। क्लियर है कि नहीं है? सो कंजुगेट बीम मेथड इज नथिंग बट इट इज एन टूल to find slope and deflection, and this beam is not existing in reality, it is the temporary structure जिसको आप अपने मतलब के लिए यूज कर रहे हो। ठीक है, कोई भी बीम ड्रॉ करने के लिए तीन चीजों की आवश्यकता होती है माय डियर फ्रेंड्स। एक होता है लोड कितना आ रहा है उसके ऊपर, एक उसकी सपोर्ट कंडीशन कितनी होगी, एक उसकी लेंथ कितनी होगी। लोडिंग की बात की जाए तो लोडिंग जो रियल बीम का M/EI डायग्राम, देखो आ गया ना M/EI डायग्राम, तो रियल बीम का जो M/EI डायग्राम है वही कंजुगेट के लिए लोड की तरह एक्ट करता है। डायमेंशन वाइज मत देखना, क्योंकि डायमेंशन वाइज तो भाई स्लोप भी शियर फोर्स के बराबर नहीं होता और बेंडिंग मोमेंट भी डिफ्लेक्शन के बराबर नहीं होता। तो लोड के डायमेंशन को न्यूट्रलाइज किया गया है M/EI से, सो दैट अकॉर्डिंगली जब आप शियर फोर्स निकालोगे तो आपको थीटा के डायमेंशन मिल जाएंगे, अकॉर्डिंगली जब आप बेंडिंग मोमेंट निकालोगे तो आपको डिफ्लेक्शन के डायमेंशन मिल जाएंगे। सो इट इज एन इमेजिनरी बीम whose loading is equal to M/EI diagram of given beam, okay, whose length is equal to the real beam। And रही बात सपोर्ट कंडीशन की, सपोर्ट कंडीशन you guys can also deduced based on real beam only, or we can say that supports in conjugate beam method are located in the conjugate manner, and how this conjugate beam is going to work I will be telling you। ठीक है, देखो before heading towards conjugate beam I want to explain the two theorems involved in conjugate beam। थ्योरम बहुत सिंपल है डियर मेरे। थ्योरम सिंपल बोलती है कि यार रियल बीम पे अगर आपको स्लोप चाहिए तो आप कंजुगेट बीम बना लो। मान लो आपको कंजुगेट बीम बनाना आ गया, ठीक है, कैसे बनाएंगे अभी बात करेंगे। मान लो आपको कंजुगेट बीम बनाना आता है तो रियल बीम पे आप क्या करो, स्लोप चाहिए तो कंजुगेट बीम बनाओ पहले उसका, और कंजुगेट बीम पे उसी पॉइंट पे आप शियर फोर्स निकाल दो। ठीक है, चलिए नेक्स्ट। थ्योरम 2 क्या कहती है कि अगर आपको रियल बीम पे कहीं पे भी डिफ्लेक्शन निकालना है तो आप क्या करेंगे, आप कंजुगेट बीम पे उसी पॉइंट पे बेंडिंग मोमेंट निकाल दोगे। ठीक है, मतलब देखा जाए तो बेंडिंग मोमेंट डायग्राम ऑफ कंजुगेट बीम इज गोइंग टू गिव यू द डिफ्लेक्शन कर्व, और मतलब देखा जाए तो शियर फोर्स डायग्राम ऑफ कंजुगेट बीम इज गोइंग टू गिव यू द स्लोप कर्व। सो दिस इज द केस। नाउ रियल का स्लोप, कंजुगेट का शियर, रियल का डिफ्लेक्शन, कंजुगेट का बेंडिंग मोमेंट। तो इसको समझने के लिए हम क्या करेंगे, हम कंजुगेट सपोर्ट्स बनाना सीखेंगे। फॉर एग्जांपल आई डू हैव सम रियल सपोर्ट्स, and accordingly we have to make our conjugate supports। criteria I have already told you कि रियल का शियर रियल का स्लोप कंजुगेट का शियर होना चाहिए, रियल का डिफ्लेक्शन कंजुगेट का बेंडिंग मोमेंट होना चाहिए। सो जस्ट टेल मी माय डियर फ्रेंड्स, सपोज इफ आई डू हैव ए हिंज सपोर्ट or a roller hinge support, suppose I have a hinge support or a roller hinge support, then you can see here theta will be there but deflection is not there। So suggest me something in conjugate support which should be having shear force but it is independent of bending moment, because the deflection in real beam is in real support is 0, so we do not need anything on the name of bending moment in conjugate support, but theta is existing here, so I need something which can bear some shear। Tell me, suggest anyone। So this is your hinge or roller hinge, so it is equal to it is equal to hinge only, or say it roller hinge only, or simply say it roller hinge only. You can see on hinge support shear force exists, but bending moment is 0 whenever your hinge support is coming in the end. Yes, Sachin is right, Daksh is right, yes, exactly, because it is a type of support which is having reaction, so it is carrying shear, but it is not having any bending moment. It's not like that your hinge support cannot carry moment. Moment can come here, but for that it should come in between, or your member must be overhang. But whenever your hinge support is coming at the end, okay, so at the end if it is coming, so it is free from bending moment, because whatever it want to rotate, whatever rotation is required to dissipate the bending moment, that much of rotation it is going to give the member if it is located at the end. Okay. So that is the case. Case number 2, suppose if we have fixed support. Suppose if we have fixed support, we all know that at fixed support slope is not there, deflection is also not there. So tell me, propose me a conjugate support where shear force should be 0 and bending moment should also be equal to 0. Do you really think is there any support which is going to carry both of these forces 0, both of these stress functions 0? Tell me, guys. Yeah, very good, Daksh. It's free and or free support or free without any support. So you have to keep this fixed portion free. Okay. I am only focusing. ये क्या हो गया? I am only focusing. This end. Don't think that it is free. I am only interested in the supports only right now. Okay. So this is free. This is free. So again, if I told you that this time I am focusing on free end, where theta exists, delta also exists, then propose me a support where shear force, भाई मैं नहीं थका, मेरा पेन टैप थक गया, shear force is there and bending moment is also there. Means you need a support which is going to carry vertical as well as movement. Anybody? It is fixed. It is fixed because fixed support is going to carry vertical force as well as moment, so it can give you both of this property. Similarly, my dear friend, if we have something coming in between like internal hinge, for that also we have the alternative. Suppose we do have real support, and what is conjugate support? Suppose we have let's say like this or like this. Roller and hinge are not going to make any difference in beams because they are not in the slope and deflection domain, because here the slope and deflection we are calculating only due to bending moment. Okay, unless it is a case of truss. Here theta is 0. Sorry, theta is not equal to 0, but delta is 0. So tell me something where shear force should come but bending moment should be 0. Tell me this case, dear all of you. It is internal hinge. It is internal hinge. Last, suppose if there is internal hinge, then you know at internal hinge what is happening. Theta exists, delta also exists. So suggest me something which should come in between, and it must contain shear force as well as bending moment. So what can be the possibility? Yes, hinge. Okay, next case, tell me the possibility. So internal hinge, it's internal roller, it's internal roller support or internal hinge support, roller or hinge and whatever, roller or even hinge. Okay, because if roller or hinge is coming in between, they are capable of carrying even bending moment as well. Okay, so that is the case here. That is the case. So can you draw some conjugate beams if the real beams are known to you? Like this is the real beam. So if I want to draw the conjugate beam here, so don't you think it is going to be same? So in simply supported beam, real beam and conjugate beam are same. But here you can see it is just like that. It is like your mirroring. So that is the reason why they call it conjugate, because in some of the structure mirroring happened. So they are conjugate ना. जैसे यहाँ पे भी आप चाहो, even you can draw this beam like this up to some extent. So this also will give you the feeling of mirroring, conjugation. Not always, but in most of the structure it happens. Now here fixed will become free, and free will become this. This will become internal hinge, and this will be roller support. Okay, here also you can see some extent of mirroring. Okay, it may happen or it may not happen. Okay, but what you can see here, this is my real beam, this is my given beam or real beam. In all these three cases, my real beam is stable and it is determinate as well. It is determinate as well. And my conjugate beam here is also, you can check the stability, and they are determinate as well. So real beam is stable and determinate. If real beam is stable and determinate, then conjugate beam is also stable and determinate. Okay. But what happened if my real beam is unstable? Suppose if my real beam is unstable, let's say like this. If my real beam is unstable, let's say like this. So what about the conjugate beam? What about the conjugate beam? So if real beam is unstable, then the conjugate beam is, it is fixed, it is free, and it will remain as it is, or at most you can make it roller. So if real beam is unstable, then you can see conjugate beam is indeterminate. Conjugate beam is indeterminate if real beam is unstable. Are you getting the point or not? Tell me, guys. Okay, if real beam is indeterminate, if real beam is indeterminate, now what about conjugate support? Fixed will become free and roller or hinge will become hinge on. So conjugate beam is indeterminate if real beam is unstable. It is unstable, it is indeterminate. And if real beam is indeterminate, then conjugate beam becomes unstable. So it is advisable to use conjugate beam technique only in case of real beam, only in case of determinate and stable beam. Okay, now let me go back to page number 1. Now you can have a reading of this page, whatever is written here. It is an imaginary beam for which loading is minus m upon EI diagram of given beam. If the given beam is determinate and stable, then conjugate beam is also determinate and stable. If the given beam is indeterminate, then the conjugate is unstable, and if given is unstable, then conjugate beam is indeterminate. This is what I have written on page number 1 of slope and deflection conjugate beam method. Isn't it? So what next? Theorem 1, Theorem 2 clear, real support, conjugate support clear. So now you can read out these guidelines to draw conjugate beam method. So M upon EI diagram of the beam is loading diagram. If M upon EI diagram is positive, then loading in conjugate beam is upward, and it is negative, then it is downward. Don't worry about this M upon EI diagram dear. Whatever you want to take, you can take that sign. अगर ये आपको डायग्राम नीचे दे रहा है तो अपनी मर्जी से ऊपर बना दीजिए, अगर ऊपर दे रखा तो ऊपर ही रहने दीजिए, पर ध्यान रखिएगा अगर आपका डायग्राम नीचे है और आप उसको ऊपर बना रहे हो, then you would be getting same sign convention as you had in moment area method. Okay, as long as magnitude is considered, there is not going to be any difference due to this m upon EI or minus m upon EI diagram here. Okay, so if shear force at a section in conjugate beam is positive, then slope at that section in real beam is also positive, and positive as per moment area it is anti-clockwise. Okay, if bending moment at a section in conjugate beam is positive, then deflection at that section in given beam is also positive. And if any condition of conjugate beam are such that the shear force in conjugate beam is represented by the slope and bending is represented by the deflection. Okay, based on that only I have drawn the table for you. Which table? This table. This table. Okay. So tell me. देखो एग्जाम में क्वेश्चन आता है, आप किसी भी मेथड से करो कोई फर्क नहीं पड़ता, आपको कंजुगेट बीम लगाना है कंजुगेट बीम लगाओ, आपको स्ट्रेन एनर्जी लगाना है वो लगाओ, मोमेंट एरिया लगाओ, डबल इंटीग्रेशन लगाओ, बट कंजुगेट बीम बनाना जरूर सीख लेना, बिकॉज एक बार ऐसा हो रखा है जब सामने वाले ने आपसे पूछ लिया था कि विच ऑफ द फॉलोइंग इज गोइंग टू बी द कंजुगेट बीम। अब वहां पे तो आप ये नहीं बोल सकते कि भाई स्लोप एंड डिफ्लेक्शन मेरी मर्जी में जिससे निकालूं, उसने आपसे पूछ ही लिया कि कंजुगेट बीम कौन सा बनेगा। Are you getting the point or not? So at least you should know how to draw at least conjugate beam. Clear है कि नहीं है? So do you want me to take an example on this? Conjugate beam का कोई example चाहते हो आप मेरे से? Tell me frankly. एक कर दूं? Okay. So let me take an example. जिसको मूवमेंट एरिया वगैरह से करना थोड़ा मुश्किल है। लेट्स सपोज दिस इज एन इंटरनल हिंज। लेट्स सपोज इट इज एन इंटरनल हिंज, इट्स डिस्टेंस इज L, इट्स डिस्टेंस इज ऑल्सो L, दिस इज A, दिस इज C, दिस इज B, and I am applying a point load here. Okay, all I need to know deflection at C. I want to know the deflection at C. Okay, so by using conjugate beam method, I need to find the deflection at C. So shall we? How we can proceed? Okay, first of all I need to develop the M upon EI diagram. So for M upon EI diagram, I need to solve this structure. In order to solve this structure, I can take the bending moment about C is equal to 0. From there, I will be getting that yes, reaction at B is coming out to be P by 2. If it is P by 2, in order to maintain the equilibrium of vertical forces, it also has to be P by 2. If this is P by 2, then again I can take a bending moment about C is equal to 0 from left hand side. From there you can get this value. This is P by 2 into L. So it is PL by 2. It is PL by 2. So if I am going to draw, bending moment diagram here, if I am going to draw bending moment diagram here, then it will be like this. It will be like this. It will be like this. Okay. Make sure that it is lying exactly under the C. Yes, it is lying exactly under the C. So this is PL upon how much? 2. Just a minute. Okay. So this is what you are getting dear here. So this is M upon EI diagram. So now let me draw the conjugate beam. So fixed will become free, internal hinge will become internal roller or hinge support, and this roller can remain as roller only. So conjugate beam for that particular beam, conjugate beam is imaginary beam whose length is equal to the real beam. Okay, fixed will become free and internal hinge will become internal roller, or make it a hinge, and it is so M upon EI diagram. You can make it as the way you want. I am making it in word, doesn't matter. So you can draw it like this. So this is the loading intensity diagram. It is PL upon 2 EI and this is PL upon 4 EI. Okay, and the corresponding points are A dash, C dash, B dash, and if you need to find deflection at C in the real beam, then in the conjugate beam you need to calculate the bending moment at C dash. So how to calculate the bending moment at C dash? Bending moment at C dash is equal to this bending moment about C dash is what? Half into base into height into 2/3 of L. So this is coming out to be, it is PL cube upon 6 EI. So this is the deflection. This is the deflection at C. You can check out. This is also the deflection at C. So deflection at C is also equals to PL cube upon, it is also equals to PL cube upon PL cube upon 6 EI. Okay. So this is a way to calculate it with using conjugate beam method. And yes, it is coming out to be negative. And here also you can check, it is also negative because it is minus M upon EI diagram. Now, and bending moment is hogging now. So half into base into height is the load, 2/3 L is the moment. So this is going to produce the anti-clockwise movement to the left of the section. So anti-clockwise movement to the left of the section we have considered as hogging, and hogging is negative for us. So this is negative only. So this minus sign is introduced just to match the sign convention. You are going to get same convention as you are getting in moment area. Okay. So this is a way. Although you can also check deflection at C or slope at B dash. Each and everything you can calculate. For that you need to find the RB dash value. Okay. So like this you can use the conjugate beam method. Like this you can use the conjugate beam method. Tell me any other wish. Anything else? Okay, so now let me move on to last method, which is the strain energy method, also known as the Castigliano second theorem. ये लास्ट है, बस खत्म इसके बाद. ओके सर, मैग्नीट्यूड सिर्फ कंसिडर क्योंकि इलास्टिक कर्व, क्या लिखा है सर? मैग्नीट्यूड सिर्फ कंसिडर करूं क्योंकि इलास्टिक कर्व क्या है, पता रहता है. हाँ, कोई दिक्कत नहीं है, सिर्फ मैग्नीट्यूड पे वो रखो, ध्यान रखो आप. मैं तो खुद बोल रहा हूँ कि डोंट बी कंफ्यूज. जो भी आपको बस लोडिंग जैसा है वो पैटर्न आपको वहां दिखाना है. लोडिंग जैसा है वो पैटर्न आपको वहां दिखाना है. क्लियर है कि नहीं है? ओके दक्ष, कोई बात नहीं, ठीक है. यू कैन ओके, नीड नॉट टू बी वरी. ओके चलो एंजॉय करो, रिकॉर्डिंग देख लेना, कोई दिक्कत नहीं. हाँ सचिन, इज इट क्लियर डियर? चलो अब लास्ट करते हैं स्ट्रेन एनर्जी मेथड. एजम्पशन सेम है, मटेरियल होमोजेनियस आइसोट्रोपिक इलास्टिक रहता है, टेम्परेचर कांस्टेंट, सपोर्ट्स आर अनयील्डिंग. Okay, it is the second theorem of Castigliano, which says the partial derivative of total strain energy with respect to load or force gives you displacement in the direction of load. This load, if it is linear, it is going to give you linear displacement, and if this load is rotational, it is going to give you slope. Okay, so indirectly Castigliano has used the rigid body equivalency in your elastic body. Like we do have delta as work done upon load and theta as work done upon torque or movement. On the same fashion, he differentiated load, he differentiated energy or work done with respect to load in order to get the deflection. He differentiated, just a minute guys, just a minute. Just a minute, I am coming back in 2 minutes. Just a minute, I am coming back in 2 minutes. ओके यस. हाँ सचिन, गर्ल है, बेबी बेबी गर्ल है. चलिए चलो चलो फिर क्या बता रहा था मैं आपको? हाँ, तो एजम्पशंस मैंने आपके साथ शेयर किए थे. मटेरियल इज होमोजेनियस आइसोट्रोपिक एंड इलास्टिक, and temperature is not constant and supports are unyielding. Okay, so delta अगर आपको निकालना है, then delta is del u upon del p dash, and theta आपको निकालना है तो theta is del u upon del m dash. Okay, like कैसे निकालोगे आप? Suppose this is p dash and this is the elastic curve. The delta is this del u upon del p dash. Okay, and suppose if cantilever beam is like this, this is theta. This theta is this much. Okay. Now the question is how to calculate the strain energy. In order to calculate the strain energy, dear, you need to see which parameter you want to calculate slope and deflection. Generally, we calculate slope and deflection for bending moment only, because the other component are quite diminished, you can say, in comparison to bending moment. But what is happening? Dear, exactly in trusses, especially in the case of trusses, the prime cause of slope and deflection is axial load. So there you can calculate the strain energy due to axial load. So basically, strain energy is universal, because even you can change the method of input. You can calculate the deflection due to shear, you can calculate the deflection due to axial load, even you can calculate the deflection due to torsional moment, shear force, anything. So all you need to give input as energy. So there can be different type of energy, like it is total energy due to bending moment, it is total energy due to axial force, it is total energy due to torque, it is the total strain energy due to the shear. Okay, so like that you can calculate the total energy. Okay, all you have to differentiate this. So suppose we are focusing on beams and frames, so there we need to calculate slope and deflection due to bending moment. So if we need to find delta is del U over del P. So what is del by del P? It is m square. It is m square into dx upon 2 EI. So it is 2m del m over del P dash upon 2 EI into ds. So by this you guys can calculate delta. So delta is, sir ji naam अच्छा ठीक है पुराना है. So delta is this much. Is it clear? So this is the way to calculate delta. Similarly, you can also calculate theta, dear. You can also calculate theta. Theta is del upon del m dash of strain energy, and strain energy is m square dx upon 2 EI. So theta is also coming out to be integration m del m over del m dash over EI into dx or ds. So these two are the tools by using which you can solve any problem in any case of structure due to bending. Doesn't matter you are working with trusses or not trusses. In trusses the input is changed. You are working with arches, frames, beams, columns, even if you are analyzing them for buckling or bending. So you can use them, okay, in order to calculate slope and deflection. Okay, so based on this, if I want to demonstrate one problem, तो कोई भी एक problem बता दीजिए. जैसे एक simple सा problem कर देता हूँ. Suppose if I want to calculate deflection at B. Suppose if I want to calculate deflection at B, if EI is constant, then what to do? Write down the bending moment equation first. This bending moment equation is basically minus P into X, and we need also to calculate its derivative, because that is also required. So now when it comes to delta, it is integration of m11 del m11 over del P dash upon EI into dx. So it is integration of minus px minus x dx over EI, and this is PL cube upon 3 EI, because whatever is the limit of bending moment function, it is also the limit of your integration. So it is PL cube upon 3 EI. Is it clear, guys? Okay, so here you can get each and every value by using the strain energy method here. Okay, so the only thing which I want to say now that you can use remember these results. Almost all of the results we have covered here. All of the results in starting now. This one, this one, this one, this one, this one. So all these standard results we have covered. Okay. So if you need more clarification and more numericals on strain energy method, you can watch my special class. Okay. because from a concept point of view I have covered a strain energy method, but yes, I know to understand the strain energy method you need to practice several numericals, at least 5 to 6 numericals you have to attempt, then only you can say that you are comfortable in a strain energy method, you are comfortable with the concepts of a strain energy method. ओके, बाकी तो स्ट्रेन एनर्जी मेथड बहुत वास्ट है. क्लियर है डियर? तो यहीं तक रहने देते हैं, बट ये रिजल्ट्स आप देख लेना, ठीक है. कोई डाउट होगा तो मुझे बताना नेक्स्ट क्लास में डियर. कल दोबारा मिलने की कोशिश करेंगे एक बार, ठीक है. चलिए, सो लेट्स कीप अप टू हियर. बस इतना ही रहने देते हैं आज. सो दिस इज ऑल अबाउट स्लोप एंड डिफ्लेक्शन फ्रॉम माय साइड, ठीक है. चलिए, कोई डाउट हो तो आप पूछिए. ओके, सो लाइव मेंटरिंग प्रोडक्ट के साथ 1:1 लाइव मेंटरिंग इज बीइंग डन विद ऑल द न्यू आइकॉनिक सब्सक्रिप्शन एंड स्पेशल क्लास. अभी काइनेमेटिक इंडिटर्मिनेसी पढ़ना है किसी को? अगर किसी को काइनेमेटिक इंडिटर्मिनेसी पढ़ना है तो अभी 7:15 पे क्लास रखी है मैंने, आप स्पेशल क्लास पे आ जाइएगा, ठीक है. फ्री होता है, ये भी फ्री रहती है क्लास आपके लिए. ओके, थैंक्स ऋषिकेश, थैंक्स. हाँ, मैंने कोशिश तो किया सब कुछ कवर हो जाए, बट तब भी मैराथन के नाम पे कुछ चीज़ें हो नहीं पाती है. चलिए, बट यस 12 घंटे नहीं 11 घंटे की वीडियो में लगभग चीज़ें सब कवर कर दी है मैंने. 90% तो कवर कर दिया है, मैं खुद नहीं बोलूँगा 100% कवर दिए मैंने. 90% आई हैव कवर्ड. ओके, एंड यू गाइस कैन ऑल्सो चेक आउट द ब्रांड न्यू अपडेट्स ऑन अनअकैडमी आस्क ए डाउट. And this is the official Telegram channel of our team, and these all are the benefits of Plus and Iconic planned here, and this is the subscription price. हाँ, अगर कल रात तक सब्सक्रिप्शन ले लोगे ना तो इस कोड पे आपको 20% मिल जाएगा. इस कोड पे आपको 20% मिल जाएगा इंस्टेड ऑफ 10%. ओके, सो थैंक्स अ लॉट माय डियर फ्रेंड, टेक केयर, स्टे सेफ, बाय बाय, सी यू सून, बाय बाय.